Good morning, everyone. I would like to begin today's workshop by thanking the DEDISA, the local municipal waste management company at the Municipality of Chania. I would also like to thank the Municipality of Chania for allowing us to have this workshop in this magnificent location at the port of Chania. And we're really grateful that we are able to collaborate with the DEDISA and having the opportunity to advertise, to communicate, and increase the visibility of the LUCRA project and the Cirque landfill project through this workshop. My name is Apostolis Koutinas, and I'm professor at the Agricultural University of Athens in the Department of Food Science and Human Nutrition. My research is focusing on industrial biotechnology and biorefinery development, the whole value chain, starting from the feedstock, the pretreatment, the fermentation development, the downstream separation and purification, and end-of-life recycling process development. Nowadays, we're introducing electricity-driven technologies in order to substitute for high temperature and pressure, acid bases and solvents in the processing of biological resources for the production of bio-based products. In order to introduce the focus of the LUCRA project and the Cirque landfill project, I would like first to make an introduction to the bioeconomy. That is actually bioeconomy focusing on the use, produce, manufacture, processing, and all of biological resources. And this is actually a part of the European economy, employing 8.2% of total EU employment, and also focusing on 2.3 trillion euros in terms of turnover. That is around 5% of EU's GDP. As you can see, there are the major sectors of the bioeconomy is actually agriculture and forestry, food and feed, as well as bio-based industries. And the bio-based industries would have different sectors, one of which is the production of bio-based chemicals and materials. Actually, the focus of bioeconomy-related projects such as LUCRA is focusing on the creation of sustainable and viable and efficient processes for the production of bio-based chemicals and materials. Within bio-based chemicals and materials, the European Union domestic production is around 3%, but the European Union holds 31% of the global market in terms of bio-based chemicals and materials. Among these, biosurfactants is one of the major bio-based products produced and used in the EU market. However, the major targets of products like LUCRA is to create platform chemicals as major options for the production, as building blocks for the production of bio-based chemicals and materials. Platform chemicals, taking the paradigm of the petroleum refineries, are actually the core building blocks are used for the production, for instance, of plastics or chemical additives by industry or end applications. So the petrochemical industry is producing several major core building blocks, such as ethylene, propylene, butadiene, xylene, toluene, for the production of the chemicals and plastics that we know today. So our focus is to substitute these core building blocks by bio-based ones. One of the major areas for the utilization of bio-based monomers and also bio-based materials, it's actually the bioplastics sector. The bioplastics nowadays can be divided into those of bio-based nature, while they can be divided into biodegradable and non-biodegradable. Bio-based non-biodegradable plastics are actually mainly drop-in plastics that are currently produced by petrochemical resources substituted by the same materials that can be produced from biological origin. But in this case, we don't solve problems of end-of-life recycling. However, in the case of biodegradable polymers, we have flexibility in terms of end-of-life post-consumer bioplastic recycling approaches. We have higher flexibility in terms of development of recycling options. But in this case, the cost is much higher as compared to conventional counterparts. The focus of both the LUCRA project and the Circular Landfill project is actually the production of succinic acid as a major platform chemical for the production of bio-based chemicals and materials. Succinic acid, it's a major bio-based building block because of its functionality and its ability to be produced from different sugar resources, natural sugar resources, by using natural microorganisms or genetically engineered microorganisms. However, its industrial implementation failed despite the tremendous effort to make this feasible because of production costs and also market development alternatives. The biorefinery map in European Union can be is actually widespread in the case of bio-based chemicals production, in the case of liquid biofuels production, as well as in the production of bio-based composites and fiber. You can see on the map on the top left-hand side, where is the bio-based chemical biorefinery development within the European Union, and on the bottom right figure, you can see the feedstocks that are currently used for the production of bio-based chemicals, as well as bio-based composites and materials. You can see that the top feedstocks that are used are oils and fats, as well as starch-derived sugars, while waste is not the major resource for the production of bio-based chemicals and materials. So projects like LUCRA and landfill is actually trying to expand the options of waste streams for the production of such bio-based products. Why municipal solid waste? One of the problems of the bioeconomy is the availability of feedstock. While organic fractions of municipal solid waste are actually already collected in central locations all around Europe, because organic fraction of municipal solid waste contain mainly food waste and also garden waste, and these are already collected, are managed by low-value end uses, such as composting, while in the bioeconomy era, we foster the utilization of such waste streams by upgrading them into industrial feedstocks for the production of bio-based chemicals and polymers. One of the big advantages of the municipal solid waste is, besides their availability and central locations all around European Union countries, it's also that there is a tax applied to citizens in each municipality, in each country, to collect the waste streams. So the collection is already subsidized in the management, so we need to turn the collection and management into collection and valorization for the production of end products of higher value, both for the society and the citizens, and also for the environment and the market, and the associated markets. Besides, in order to strengthen the availability argument, we carried out a few years ago a mapping using Eurostat data in order to showcase that the organic bio-waste is available at quantities that can support the development of biorefineries. So considering the economies of scale target for the production of succinic acid, which is around 30,000 tons of annual production capacity, if we consider a yield of 0.6 grams of succinic acid per gram of sugar conversion, then we need around 50,000 tons of carbohydrates from the organic biowaste availability. And we found out that all around Europe, in every European country, there is sufficient availability of carbohydrates from the Municipal biowaste in order to produce bio-based succinic acid. So we don't only have centrally located facilities where this feedstock is collected, but is also available at quantities required for satisfying economies of scale, which is actually one of the most critical issues for industrial development. Before the LUCRA project, the idea of the electrochemical extraction of succinic acid in situ with production by fermentation was developed in the PERCAL project, where actually we first demonstrated a low technology readiness level of 4 to 5, the potential to produce and extract succinic acid in situ. And the advantages of electricity-driven technologies is that we minimize the utilization of bases, acids, and unit operations required in the downstream separation and purification stages, making succinic acid production more environmentally benign and also more cost competitive. The products that were developed in the PERCAL project to show the potential for biorefinery development for municipal biowaste was actually the production of biosurfactants for cleaning, from cleaning products, from the lipids and protein fraction of the municipal biowaste, and also utilizing the carbohydrate fraction to produce either lactic acid or succinic acid or ethanol, or in order to be used for the production of hot metal adhesives or polyurethanes from succinic acid. So, today's workshop actually is to showcase the LUCRA project representing a major innovation action project funded by the CBE JU and for the production or for the development of bioeconomy products, and also the nationally funded Circ landfill project that is led by the Agricultural University of Athens, together with the participation of the DEDISA Solid Waste Management Company, together with the Aristotle University of Thessaloniki, the National Kapodistrian University of Athens, HIMAR, that is focusing on the production of bio-based adhesives for wood panel applications, and also the company Achaika Plastika that is focusing on the production of mulching films. So the target of the Circ landfill project is to develop bio-based adhesives from the protein fraction of municipal biowaste for the production of biochar for lignocellulosic prunings, for instance, and also mulching films from succinic acid through its conversion in polybutylene succinate. So creating biodegradable and bio-based solutions for 3 market sectors. In the case of the LUCRA project, we have collaboration led by the Biobased Europe pilot plant, the coordinator of the LUCRA project, together with the collaboration of Monti Nutra, the FCC, the Agricultural University of Athens, University of Ghent, Hydrom, Covestro, and also the CNR from Italy, and also our a company responsible for the communication, which is Steinbein's Europa Centrum. So the target of the project is actually the production of succinic acid and Ainuevo. So the target of succinic acid production in the LUCRA project is the production of polyester polyols, polyurethanes, and bio-based resins as bio-based products that can substitute conventional counterpart with higher sustainability and cost competitiveness. So I'm thrilled actually to open this workshop, and the following presenters will actually present different aspects in these projects in order to showcase the potential bio-based product development for municipal biowaste. Thank you very much, and I'm open to answer to any question. Is there any question from the online participation? Okay. All right, so we can move to the second presentation.
Good morning, everybody. I would like to welcome you in Chania and thank you for being here today. My name is Christina Tsamoutsoglou and I am the Deputy Manager of Leachate Treatment Plant at the DEDISA. Today I will try to explain in a few words how the DEDISA transforms municipal solid waste into valuable materials by applying circular bioeconomy principles. What is circular bioeconomy? The circular bioeconomy promotes sustainable use of biological resources by closing material loops and reducing waste. Throughout this presentation, we will see how this concept is applied practically to municipal solid waste management. Now I will introduce you the DEDISA and its important role in managing waste locally. The DEDISA is the main entity responsible for the integrated municipal solid waste management in the regional unit of Chania. Its activities include waste collection, waste treatment, materials recovery, final disposal, and of course the public awareness. Serves a population of over 150,000 permanent residents, where this number in the summer months is duplicated. The DEDISA is coordinating with waste services across the 7 municipalities with a focus on compliance and social responsibility. The collection and transportation of various waste streams are carried out in close collaboration with the municipalities. The system, except the mixed solid waste collection, includes a comprehensive source separation system as blue bin for paper, plastic, aluminum and metals, yellow bin for the glass, brown bin for the bio-waste, purple bin for the textiles, bulky waste collection, green waste collection, electronic equipment collection, and additionally we have a door-to-door collection service only for the residents of the old town of Chania. Thanks to this collaboration with the municipalities, we are able to recover significant amounts of materials. Mixed waste collection and treatment form the foundation for recovering valuable materials and minimizing landfill disposal. The process involves mechanical treatment with advanced sorting technology, like rotary sieves, optical separators, robotic separators, and of course we have a hand sorting process for the quality control of the recoverable materials. Also, there is a full equipped composting facility for the utilization of the organic fragment from mixed solid waste. The process of blue bin follows the same treatment line as mixed waste, but different time intervals. And as we saw in the previous slide, source-separated recyclables are collected through a targeted bin system. These materials undergo advanced sorting processes to ensure high-quality recovery and recycling. The residues from the treatment of mixed waste and the source-separated recyclables are directed from the landfill. Bio-waste separated at the source is collected daily and subjected in an open windrow composting process to produce high-quality compost. In this way, we're contributing to nutrient recycling and soil health in line with circular economy goals. Bulky waste and green waste streams are collected and treated separately. These waste categories require specialized handling to maximize recovery and minimize landfill disposal. Bulky waste is sorted into recoverable materials and non-recoverable materials. Non-recoverable bulky items are shredded before landfilling to minimize their volume. Nearly the entire quantity of the green waste is shredded and directed to the composting processes. Few words about composting. Compost production integrates organic waste from 3 distinct streams, combining them to create a high-quality soil amendment that supports sustainable agriculture. The organic fraction from mixed municipal solid waste combined with shredded green waste and is directed to the fast compost tank, where it remains for approximately 40 days. Subsequently, the material undergoes a refining process and is transferred to the maturation area where it matures for an additional 8 to 12 months. As we said before, for the organic fraction derived from source-separated collection, shredded green waste are also added, and the mixture is subjected to open-type composting for maturation. The last year, we produced a new material that we call mulch. Mulch is derived from shredded and semi-composted green waste, and the suggested use of this is as ground cover or mixed with soil as soil improver. At this point, it should be noted that all processes are controlled with continuous monitoring of moisture and temperature to ensure optimal composting conditions. Also, we are responsible for the standardization and packaging of different soil blends, as you see here, designed for diverse agronomic uses. Landfill management and leachate treatment. The landfill site is carefully managed to minimize the environmental impact. Within the landfill, waste is subjected to daily compaction to minimize its volume and consequently covered within inner materials. The leachate treatment system is an integrated tertiary treatment facility that employs reverse osmosis technology. The treated wastewater consistently meets the strict limits set by Greek legislation for the reuse, ensuring environmental safety and regulatory compliance. Quantified recovery outputs. This slide highlights the significant annual production of compost, reflecting the effective organic waste valorization at the DEDISA. The volumes confirm the system capacity to convert organic fraction into viable soil amendments. Moreover, the recycling quantities for collected materials, such as paper, different categories of plastic, metals, are quite high, demonstrating the efficiency of the source separation and material recovery processes. These recovered materials contribute to resource conservation and landfill diversion. And of course, we have the public awareness. The DEDISA actively promotes environmental awareness through school programs, citizen participation initiatives, and distribution of leaflets with instruction on reusing materials, reducing waste production, and recycling. We believe that public engagement is the key to the success of source separation and circular economy practices. Last but not least is our participation in European and national projects. The DEDISA has participated on multiple European and national projects aimed at improving waste management, reducing greenhouse gas emission, and advancing innovative bio-based solutions. These partnerships strengthen regional capabilities and align with broader sustainability goals. Mr. Koutinas has already presented the Circular project, so I will pass this slide. Our next steps include investment in advanced sorting and bioprocessing technologies. We are allocating capital into state-of-the-art sorting and biological treatment technologies. These investments improve recovery rates, reduce contamination, and enable the production of higher value end products. Strengthening the collaboration with municipalities and universities. We believe that cross-sector collaboration is critical. By working with local governments and universities, we can pilot innovative solutions, validate results, and scale up successful model efficiently. Transformation into a circular resource management hub. We are shifting from traditional waste handling to becoming a circular resource management hub. This means designing systems that retain value, extend material life cycles, and reduce dependency on natural resources. Maximization of environmental and financial value from waste streams. Every step we take must deliver both environmental and financial returns. Through integrated planning and operational excellence, we aim to unlock the full potential of waste as a resource. And in conclusion, we're not sure, but we believe that the DEDISA's model successfully demonstrates a replicable and sustainable approach to municipal solid waste management aligned with European circular economy goals. The integrated system enhances resource recovery, reduces emission, and supports regional resilience. Thank you very much for your attention. I'm here with my colleagues to answer in any question you may have.
Thank you very much, Christina. Robin?
I have one question. It's a beautiful system coloring. Yeah, I'm coming from Holland. Only 3 colors at my home, but you have 7 different colors and for the sorting of waste. I have one question on the blue color.
Okay.
So you have a blue bin. So mostly it's a plastic, and when I see your overview, I'm wondering what be the next step when you collect all these plastics, what will be our next step? Is it burning or recycling or something else?
As said Mr. Koutinas before, our goal is to utilize these products. So the best is to optimize the system of the blue bin to recovery better qualities products. So the number will be bigger, it will be an income for us. We don't have in mind something else.
Okay, thank you. Most of the plastics are not clean anymore. They are contaminated, so you have to treat the plastic before you can reuse. So that's I'm wondering, because a lot of people are working on this topic, how to convert this plastic waste into valuable chemicals or something else. But yeah, this first step, I think, is already very important. You sort all the plastic from other waste. Thanks.
Okay, thank you very much.
Good morning, and thank you for the presentation. I come from Italy, where we have been a big discussion on the use of compostable, single-use packaging materials, for example, which you can actually find in the bio-waste, because people will throw it, you know, in the...
Yes.
Do you handle this kind of problems, or finding, you know, not paper-based, bioplastic-based packaging in your bio-waste? And just a second, not question, but a curiosity. Which is the final destination of textile collection?
Okay, I will answer the second question. We are cooperating with private sector, and it reuse the textiles, or it's sent them to in Africa. For the first question, we have the same problem. We have a refiner step, but I have my colleague here, Mr. Hazirakis, that he is responsible for the composting process, to explain you whatever you want.
Dimitris, also Dimitris Moutousidis from Himar.
Thank you for the presentation. Are there any plans to expand your activities beyond the city of Chania?
No. No. We are the only one, and we do everything.
Okay, thank you.
You're welcome.
So, I think it's time to move to the next question, because we can elaborate further during the panel discussion.
Okay.
Thank you very much, Christina,
you're welcome.
for your presentation. Tanja Meyer from the Biobased Europe Pilot Plant, the coordinator of the LUCRA project, will present the LUCRA project and also innovations achieved by the Biobased Europe Pilot Plant in Belgium.
Thank you, Apostolis, for the nice introduction, and thank you, DEDISA, for having us here. It's very a pleasure to be in this wonderful location. I'm sorry for the people online that you cannot see it next time. Please follow our invitation to come on site. So I would like to present indeed some of the insights from the Biobased Europe pilot plant that has been developed in the LUCRA project. We are just in the beginning of the project, but I think there are already very interesting results that we can share with you. So as I said, my name is Tanja Meyer. I'm from Biobased Europe pilot plant. For people that are not familiar with this entity, we are what we call an open access, multi-purpose pilot and demo facility based in Ghent, Belgium. And we scale up technology that are bio-based in terms of processes and products, so like fermentation, also gas fermentation, biocatalysis, downstream purification and recovery, and also green chemistry. And we do that from technology readiness level 3 to technology readiness level 9. So again, I'll give you a short introduction to the LUCRA project. It's about the sustainable succinic acid production, which are going to use an integrated electrochemical bioreactor and renewable feedstock. It started in summer 2023, and it's going on for 4 years, so we are quite good, almost halfway. There's a CBE JU contribution of around 5 million euros, and Biobased is the coordinator. In the beginning, of course, we are focusing mostly on the municipal solid waste and the wood side streams to produce them into bio-based succinic acid. So LUCRA is consisted of 13 different partners from 7 different countries all along the value chain. It's really, really nice because we basically can cover the whole value chain with 3 RTOs, 4 SMEs, and 2 large companies that are involved, and also 1 NGO, as already also explained by Apostolis in his welcome speech. So these very unique 13 partners are on a mission to really span the fully entire value chain from feedstock to final product. What were the challenges when we started in the beginning? So what was the motivation of us to basically write together this proposal, this project? So the main idea is, of course, to shift from fossil-based chemistry into bio-based chemistry. So the re-evaluation of the reliance on fossil-based chemical building blocks, we are trying to reduce them step by step. It's a very challenging journey, but it's very necessary. And then, of course, we do that by valorizing the organic waste streams and the sawdust. At the moment, they are still underutilized, and they are also still not fully explored. So the general challenge here is actually also to, across all bio-based materials actually, the higher price compared to fossil-based alternatives and the lack of regulatory support are also very significant hurdles. So there's a strong need for the technological advancement and infrastructure improvements that we are going to tackle, and that are also not only mentioned in this one and in the CBE program, but everything for every stakeholder that are connected into the bio-based economy. So when LUCRA started, let's say on proposal level, the novel approach to waste valorization was one of the key pillars, so kind of a synergistic treatment of relevant waste streams, as said again, the bio-waste and the sawdust from Montenutra, and also to further elaborate and do a technological validation of thermal hydrolysis, enzymatic hydrolysis, to extract valuable compounds such as sugars and nutrients from these various side streams. Also, the third pillar, the succinic acid as a versatile platform molecule, with the applications across many different industries, as we also heard before, are our targets. So here I present the innovation areas in a nutshell that we have within LUCRA. So I always start to explain that we have 4 pillars in LUCRA. So first one is the feedstock pre-treatment with the 2 organic streams that we already heard about it. The biotechnology itself with the microbial fermentation for checking different strains and looking at their potential for further scaling up. But also on the same side, the DSP, the downstream and purification approach that we're targeting with the membrane electrolysis and the extraction. And then on the last 4th pillar, the bio-based products itself, also represented by 1 research institute and 1 industrial end user for the bio-succinic acid, polyester and polyols, and the pools. So going further back to the challenges and needs and hurdles, last year, together with the Waste to Funk project, which was also targeting lactic acid and biosurfactants, we did a co-creation workshop with around 30-35 participants, and also online. We had an open survey because we asked them the question, now we know everything about the feedstock and we know we have to valorize it, but what does it actually take? What do we need to make this value chain work? So we had identified 2 main audiences for this co-creation workshop, for the survey. On the one hand, of course, the feedstock owners itself, or the feedstock collectors, and on the other hand, of course, the technology providers. So they are still basically 2 different groups that have to find each other and talk to each other and talk about the same language. So we were wondering, what does it take to make this value chain work? So I have now 4 slides with me. The first one is about the feedstocks availability scheme. So let's talk about what has these two groups in common. So of course the availability has to be there. That's a demand from both sides, and they have to be correctly mapped out as well. But what are the sometimes small differences, because the devil is in the detail, where the two different stakeholder groups are having a different opinion, let's say. So for feedstock owners, quantity, quality, and also as said, the availability scheme is of highest importance, whereas for the technology provider itself, it's very important to know where is this feedstock available, so the geographical distribution, seasonality, so when is this feedstock available, and very high rated was also the influence on their current running or developed process itself. Quantities, of course, needed in volume and timing. For feedstock owners, it was very important at first hand, of course, to valorize their residue streams at also an industrial scale. So for that, they really have to know precisely the volume that is available per month or per week or per year, and also to ensure basically a continuous supply and the specifications. For the technology provider, on the other hand, they basically have to plan around their process and their production around the provided availabilities, because they, on top of their running process, they have to multiply the incoming streams to really secure a robust and strong supply chain to their clients and end users. So if you look at feedstock characterization, we asked the feedstock owners, did you actually characterize your side stream or your waste? So, and surprisingly, it was only 25% that fully characterized it, 50% did it to the half, and actually 25% did not characterize their waste stream. So they basically don't know actually what they are offering. For the technology providers, it was of course a key factor, the cost and the fit to their process. In common for these two groups were that the demand or the question for the characterization in terms of maybe a specification sheet was there, and because this would be the main driver for starting actually trials, for starting communication, for starting the proof of concept from the value chain along. So we basically made a recommendation. The first one is that there really need to be a very clear proposition to valorize the co-products that are coming from the feedstock owners. So they basically have to set in place a dedicated characterization and analyzing of the feedstock, including the availability in terms of very detailed information and detailed specifications. And the second recommendation we did is about including the co-location or the location of production for the technology provider from a very early stage from the development of the technology on. A third aspect were the regulatory aspects. So again, for the feedstock owner and for the technology provider both, we asked them on the quantitative approach. For feedstock owners, they said 60% that they were affected by regulatory and compliance issues, whereas that was 100% the case for every technology provider that we were asking. The feedstock owner mainly struggled with the waste legislation, which is not surprisingly, and also the difficulty to have a clear outlook how it will be handled on European or national level in terms of the status assigned to these streams. Plus another one was the administrative burden that comes with all this regulation and legislation on top of a feedstock that is basically already costly to handle. Also, the technology provider has a very political driven interest. So the quality grade that is assigned to the product, if they use a specific residue side stream, is sometimes in counterbalance to the legislation in terms of a technical product or a food grade product. So the impacts, that's the second point, on the novelty of the end product also affect the technology providers, if it's a scale-up or SME, the dossier's constitution, if it's talking about food-grade products in the end, or also investors' interest to invest in the company if it's a new innovation. So we made a recommendation that to the policy regulatory audience as well, to rather make an outcome-based policy rather than a prescriptive policy. So in that way, it will be allowed to any regulated parties to choose the process. So it will better meet the requirements and increase the flexibility to introduce new technologies, processes, and procedures. So that's the fourth consideration. We talked to our audience about the life cycle assessment. So surprisingly, from the side of the feedstock owner, only 20% actually had a complete life cycle assessment done of their products, and some had a partial LCA. I don't have any number on that. And from the technology provider side, for their process or products, at least in our audience, 0 people had a complete LCA, but some already had a partial LCA. So also for life cycle assessment, we said that there should be an agreement on the relevance working on LCA for both the feedstock owners and the technology providers, because it's a very, very essential tool to inform potential investors and customers of the technology providers as well. It's really convincing. So in terms of how can it become convincing that there's a new bio-innovation that is going to market, the credibility for the customer, clients, or investors is of utmost importance. So we recommend to the feedstock owner and technology provider to really do the work and invest into a complete and fully validated life cycle assessment. So that's the last slide on the overall conclusion from the challenges and barriers. So of course, all stakeholders that we talked about, they were also already active in the bioeconomy, so it's not surprisingly that they emphasized the importance also on economic and technological barriers to improve the infrastructure itself and to foster a supportive regulatory environment. So 2 points more in detail: to streamline across Europe and on national level the waste regulations to clear out the residue streams which can be valorized on one hand, to really eliminate any gray zones from the legislation in order, or best way to simplify it in the implementation at member state level, at national level, but also European level. So that will lead to, of course, decreasing for investors. It will streamline the strategy for the bio-innovators, for the technology providers, and hopefully it will really boost the collaboration that is not there yet between the feedstock owner and the technology provider. And as a second big point, also the consideration and the potential to create new residue side streams, to think about new business models, maybe to reduce the waste management cost then for non-competition with the food versus the technical projects. And of course it will bring a very high impact, or could bring a potential very high impact, especially for urban and industrial areas, to have a very detailed look in the case very locally for new business models. Okay, thank you very much, and I would be happy to take any question of yours.
Thank you, Tanja, for the presentation. Is there any question from the audience? Is there any online question? No? So if there is no question, I would like to thank you, Tanja, once more. And now we can move back to the previous speaker, Marina Navarro, who is representative from the FCC Medio Ambiente, and will present the FCC case for the valorization of municipal biowaste.
Good morning, everyone. Thank you so much for inviting us here to talk about this topic. And first of all, I want to say sorry for the previous problems, technical problems. I want to introduce the topic by saying our plant is located in Madrid Center, in the city of Madrid, and we send our products. We produce biogas and digestate, and we send to other plants in the complex, and also our rejection for another plant to manage them. In total, we are 9 plants in Valdemin Gómez Technology Park. Our process begins with the reception of the organic fraction of the selective collection of the municipal solid waste. This is the brown bin in Madrid City, and this after undergoes a pre-treatment. Then a dry mesophilic and anaerobic digestion to produce biogas, and the digestate is dehydrated. After the biogas and the dehydrated digestate are sent to another plants to valorize them. And we have also 2 auxiliary services. We have a leachate treatment plant and advanced biofiltration system to manage the odors. In general, the main objectives of the biomethanization is to reduce the landfilling in favor to a circular economy, producing biogas as a renewable energy source. But in a city like Madrid, with more than 3 million inhabitants, we generate more than 1 million tons of waste annually. It means facing some challenges for the management, recovery, and valorization of those wastes. The first, we think, are the current infrastructure. In this picture, you can see the current trash cans that are located nowadays in Madrid City, of which only of those are destined to the organics collection. In a city like Madrid, there might be not enough trash cans, but it should be noted that this initiative, the selective collection initiative, is so recent, so we think we have room yet to improve and optimize this actual infrastructure. Although the civic effort is encouraging because of the purity of the brown bin, this 20% of impurities means approximately 250,000 tons of impurities we receive annually in the plant. Even the cleanest fraction from large producers like Mercamadrid are not free of impurities. That means an exhaustive pretreatment of waste and a hard maintenance task in the equipment. Now the arrival of bioplastics as a consumer material also poses a challenge that FCC is facing through the project Prosper. So we have to found the potential of the bioplastics for the anaerobic digestion, or maybe optimize the pretreatment to separating the bioplastics from the main waste stream. As it's impossible to completely purify the waste during the pretreatment, improper deposits are formed in the bottom of the digesters. So maintenance tasks are necessary in here too to recover the useful volume in the bottom of the digesters. This is also a problem in the purity in our digestate, because we send it to another plant. FCC is running. It's called Los Cantiles, and is next to this plant, and they try to compose from our digestate. So if our digestate is not so purity, they have to face a challenge again to purify this raw material. This amount of impropers can be partly attributed to public awareness. So I am going to show you some sentences, phrases and myths that illustrate the shortcomings the society still have about recycling. This is the first, and it faces the lack of clarity or confidence in separating waste, because people doesn't even know which type of wastes are in which trash can. Or this is a very common myth, because people doesn't even know that there are different trash cans that pick up different wastes, so they think, well, people just mix them all, so it's pointless to separate it. Another one is the confusion about the organic waste collection, because as I said, this brown bin in Madrid City is a very recent initiative, so the brown bin is not yet in the social imaginary. So we have to educate the society. And last, we have the shifting responsibility people because of they thought that individual efforts are not important in a global view, and they think the big companies are the most responsible of this pollute. And to finish with the citizen awareness, we have those that doesn't even know that they can recycle certain types of waste, and so they mix them in the same trash bag. To promote social awareness, some initiatives have been implemented. The first is the continuous educational programs like this, which is the latest campaign in Madrid City that aims to teach people how to separate well the organics. Also in other cities in Spain, but not in Madrid, they are implementing these initiatives like a mobile application that rewards people that are recycling in a good way. So they give them discount coupons they can use in supermarkets or restaurants when they recycle properly. And finally, we think it should be important to invest in improvement of the number of and accessibility of bins, and providing information about how is really managed the selective collection in our city. Regarding the policies, we have to face also challenge that involves the development of biogas as a renewable energy source. The roadmap, the biogas roadmap, is a document made from the Spanish government that explains by the way to follow to multiply by 3.5 the biogas production in Spain by 2030. However, some measures have not been implemented yet. This is because of expensive processes, slow procedures, and the lack of regulations about building new biogas plants. This is the responsible of Spain to be in the bottom of European Union in biogas production, when we actually have potential to be in the top. Also, the lack of information about this topic to the people make people complain about biogas projects because they are fearing that others or the manager of the plant, the usual manager of the plant, could decrease their life qualities. For that reason, Spain and Madrid still have a strong dependence on landfilling and incineration, but these new initiatives claim to reduce them to 10% within 10 years. To encourage this purpose, we have on plant an R&D center called DEDISA that supports the transition to circular economy by the creation of new processes and value-added products. We are currently developing some projects, and one of them closely related to the circular economy is the LUCRA project. This project aims to recover urban solid waste and wood waste for the production of basic chemicals, such as succinic acid. To this end, an innovative fermentation and hydrolyzation process has been developed and optimized to obtain these chemical products without depending on fossil resources. As a specialist in waste management, FCC roles in LUCRA has been to analyze the availability and composition of biomass based on seasonality and origin, and we have studied three flows: large producers as Mercamadrid, private clients as supermarkets, and the householders. The high presence of organics was detected in summer and in Mercamadrid stream. We have also participated in the characterization of waste, and we have detected the most significant fluctuations in moisture, starch, lipids, and sugar in different seasons and streams. Finally, we have optimized the pretreatment by adding a depacker, which separated the organic material from the rejection, facilitating the rest of the stages in the process. Okay, this concludes our overview of the most important challenges we face day to day in a plant like Las Dehesas. And I want to thank you so much for your attention. I will be So pleasure to answer any question you may have. Thank you.
Thank you, Marina, for the presentation. Is there any question from the audience?
Thank you for the presentation. I was just wondering about these compostable plastics. So what kind of problems do they cause for you when?
Well, this project I mentioned about bioplastics is called Prosper, and we are developing this project right now. So we don't receive in our plant, we are not valorizating in our plant currently these bioplastics, but we are trying to find this potential to the anaerobic digestion of this material, or if it's not possible, to separate it from the main waste stream. So now we are only trying to develop and find the potential of this material. We are not working with that material in the plant nowadays.
Okay, thank you.
Any other question? Okay, thank you very much, Marina. Now we can move to the next presentation from Professor Korneel Rabaey from the company Hydrom, who is also professor at the University of Ghent, who will describe the potential of microbial protein production from organic side streams.
So, Kalimera, good morning. It's really nice to be here in beautiful Crete. So I want to talk today a bit about microbial protein. My hat today is Ghent University, not Hydrom, just to be very clear. I have different affiliations, but I want to talk a little bit about the work we've been doing on developing new protein sources. So the menu of the day is we're first going to talk about how you can make more sustainable protein shakes and how you can get this from CO2, carbon monoxide, and also organic side streams. And we'll look a little bit how that makes happy salmons and how we can even wrap up these salmons in the same protein. So there's been a lot of attention in the past years on producing microbial proteins, so new sources of edible protein from side streams. And the key driver is this very simple observation, in a way, that today, the way we provide our protein, we have to produce from mainly fossil inputs with Haber-Bosch, a lot of nitrogen that we turn into urea. We use it as a fertilizer in agriculture. And after these nutrients have gone through agriculture and ended up as food and have been consumed, what you can see is that there's a lot of nitrogen coming in. It's around 135 million tons per year into agriculture to make protein. But only a small fraction on that, the yellow line, is really ending up as food. So this is a very inefficient way of supplying the ever-growing demand of protein. And so one new source of protein, which has been existing for a very long time, more than 100 years, this has been on and off used, is microbial protein. And microbial protein is just microbial biomass which can contain up to 80% of protein. And you already eat, of course, bacteria every day when you eat cheese, when you eat bread. It's all fermented foods. So we derive microbial biomass from yeast, bacteria, or algae, and we can use it both as food and also as feed. And actually, microbial protein is very interesting, and we'll get into that later as well, because it has a very suitable amino acid profile for our nutrition. It's actually a much more suitable amino acid profile than typical sources such as soy that you typically associated with alternative sources of protein. Now, in view of time, I will not take too much time, but there's several drivers why microbial protein is a hot topic at the moment. First of all, you grow on different substrates, microorganisms, you harvest them, and this leads, because you do this in an engineered environment, to a very high nitrogen to protein conversion efficiency, almost 100%. You reach a high productivity. you can produce up to about 4 kilograms of protein per cubic meter of reactor per hour. And if you compare this with arable land, well, you need about 2 hectares of arable land on average to produce a ton of protein annually. A third thing that for sure will play here in Crete as well, because you do have also a large water shortages, is that the water use for this protein production is a lot lower, about 98% lower than current alternative sources. You can produce these microorganisms independent of climate and location. You can use many different feedstocks that associate with the microbial diversity that exists. And also it's often easier to accept as a product. It's a blend-in, it's a powder, it's a processable product, which is easier than, for example, insect protein, which has been pushed a lot in Europe, but which is not really taking off. So in the Ghent area, we have an ecosystem that is very interesting to look at alternative sources for bioproduction. And so we have a harbor where also the Biobased Europe pilot plant is. And in this harbor, you have a lot of CO2 and carbon monoxide emissions. And those are being increasingly converted to intermediate building blocks, such as formate, methanol, methane, and also ethanol. And so this ethanol is currently used for fuel. So since about a year, we are the proud, let's say, local owners of this plant, which is the Stilanol plant that produces of the blast furnace gas of ArcelorMittal, a steel company, ethanol that is being distilled up to a fuel quality and then sold off at a higher value because it's a biogenic considered ethanol in parts. But we looked for about 8 years now on how this ethanol, when it's coming, we can give it a higher value. And so in the SEMPA project, we took this ethanol, and rather than stimulating an initial distillation and purification to fuel grade, we take the ethanol as it comes from the microbial production and immediately produce from it a microbial protein to increase the value of the product and also to diversify the outflows. So in the SEMPA project, we did the typical things that you do when you have a new development. So we characterized what is pre-distilled ethanol, this direct ethanol produced from microorganisms, is like in terms of composition. We created consortia of microorganisms to grow on it. We scaled it up with biobase, and then we evaluate its use as fish meal, both for salmons and for prawns. So I will not dwell too much into the details of the research, but this is more or less a kind of a proof that you can grow microorganisms as well on this ethanol you make from the blast furnace gas than you do on a commercial ethanol. It comes at quite a nice growth yield, up to 60% of the substrate ending up in the product, both for commercial sources and the pre-distilled ethanol. And it has a nice, appreciable protein content. But what's also interesting, this is a photo of these microorganisms, and they don't look like how you typically think about growing microorganisms. You were probably expecting something white. These are bright red. So we have selected microorganisms that not only grow really well on ethanol, they also produce other products, colorful products like carotenines. And these like this beta-carotene and others that you have produced by these microorganisms are very attractive for feed purposes. For example, for salmon, they give the color to the salmon, and that creates an added value. So then with our partners, we looked at what this protein was really like. So we scaled up the process to about 1,500 liter scale. And then look, this is quite a dense table, but on the right-hand side, you see fish meal as a reference. And fish meal is a product that for about half is derived from wild-caught fish. So we catch a lot of herring in the North Sea, and that herring has no other purpose than to be grinded and fed to salmon. And so this is a source that has to be replaced because it's not sustainable. So what you see next to the line of the fish meal is the line of the scale-up batch we did in 24, and you see the amino acid composition. And the amino acids that are indicated in red, they are so-called essential amino acids. There are amino acids that have to be there and that are not present in plant-based sources typically, and that's what's creating the value. So we produced a protein that actually had a higher content of these essential amino acids than fish meal, which is very interesting. You have your different color compounds that are attractive, and the content in the cells of protein was about close to 70%, so very high protein content. Then this product was spray dried and provided to a batch of salmons. I will only talk about the salmon today and not about the prawns. So in salmon, about 50% of its feed is this fish meal at the moment. So in a negative control, we decreased this fish meal supply to about 10%. And then you had a positive control where you added 5% of this microbial protein. These are not small studies to do. So as you can see in the study design, if you have 3 different diets, you already end up with 18 tanks with about 42 salmons each in order to do the analysis. You have to look at their growth, their feed intake, the microbiome, how the gut is affected by these novel protein sources. But to our pleasure, what we found is that microbial protein, as produced here from this ethanol, was a really attractive product for the salmons. They had a very high feed conversion ratio of a bit more than 90%. That means that if you feed a kilogram of such protein to a salmon, you get 920 grams of salmon growth. So it is a very efficient way of converting a product like this microbial protein into fish, into a salmon. So these were the results as a demonstration that you can produce these products all the way to reach a food and feed grade product, and that it really works for salmon and it also works for prawns. Now here in this workshop we're looking more at organic waste, so I also want to give you some information on work we're doing on organic side streams. And in Belgium, one big organic side stream we have is grey starch. So we have a booming potato industry, which is a global billion-euro business. And so annually about 48 million tons of potatoes are being processed in Europe, to the fries, the chips, everything you can imagine. But with that comes quite a lot of waste. And so one of these wastes is grey starch. So there's about 2 million tons of grey starch, and grey starch is a residue that is not attractive anymore for any food or feed purposes at the moment, because during the processing of these organic containing waste streams, you have a heating up for the blanching. Then the product is colored through different reactions. That's why they call it a grey starch. And so it has a low value use at this moment, which is a pity, because if you look at the content, there's a lot of carbohydrates, proteins in there, some fats. So it's an interesting stream, but like our local plant has about 80,000 tons of this waste per year. And this is going to low value and uses at the moment, such as biogas production. And so, of course, in view of the talk here, we look into how to convert it into microbial protein. So as a production line, just to give you an idea what has to be done, first you need a pre-treatment, which can involve some dilution of the stream, as it's very concentrated and jelly, then a hydrolysis or a fermentation. So it's either an enzymatic hydrolysis to release the sugars, or you can do a fermentation to release all the organics as organic acids. You separate the residual solids, and here we just filter it for sterilization before we go into the microbial protein production, which is a normal, if you think about it, aerobic production reaction, an aerobic fermentation. You have to amend this wastewater a bit with nitrogen and vitamins as needed. And what we use is an organism called Cupriavidus nicator. That's maybe not known to most of you, but it's a so-called grass-listed organism. It's a microorganism that is already approved for use in food. So if you grow this microorganism on a stream that has a feed or food-grade properties, it is doable to get this finally approved as a feed or a food product. right? So what we do in the European project AgriLope, I forgot to mention, this is funded by Europe. We look at the growth of the Cupria vitis on synthetic and real streams as we generate from the hydrolysis and the fermentation. So we evaluate, okay, can they grow on the organic acids and the sugars you get there? And do you get a good protein content? And what we see is that, similar to the study I presented before, you can produce microbial protein also here with contents up to about 70% in the cell, which is a very high protein content overall. So, the last part of my talk, I want to shift gears to what else you can do with protein. And the reason that we're looking at other outlets than proteins for feed and food is that it is a long route. You know, if you make a new product like this, even if you use a known microorganism, you will have to put it into the market as a novel food, which has to go through all the EFSA regulation and approval processes, which takes years, and which is hard to do if you don't have sufficient scale. So that's one of the challenges, of course, in getting industrial biotechnology, new biological production processes up. You need approval. But approval is only useful if you have scale. And I saw before in the talk that there's like 8,000 tons of a waste stream available here in Crete. That's way too small to do a meaningful production process. You need scale. So what are potentially faster routes on getting such products on the market? Well, for that you have to look what else you can do with protein. And so the same protein that you would produce for feed and food can actually be used also for packaging. Actually, in food films, now, they are multi-layer packaging, and very often it will have a layer of protein that can come from wheat or other sources. And why do we put protein in packaging? Is because protein have unique properties such as very low gas permeability. So if you package meat or strawberries, then the protein film is actually keeping the oxygen from the air away from the product much better than many fossil-based analogues. So proteins are attractive polymers, and they're considered as true bioplastics. They are both bio-based and they're biodegradable. But today they're being produced from food sources, and of course the challenge is to produce these from side streams so you don't have a competition for food. So in the past years we had in Ghent a project called Promipol, in which we worked together with quite a few partners, and I'm just going to show you the small proof of concept that we did at the time. So we managed to grow different proteins, both conventional cultures that we use in Ghent on ethanol, methanol, and also with phototrophic microorganisms, so using light as their energy source. And if you have phototrophic protein, it gives you this very dark film in the middle, which is hard to use. But if you have a dark production process, you can see you get these yellowish films, which you could process and purify further. And so it's very interesting. What we managed to do is produce different types of plastics already by using different microorganisms and feedstocks. So they have different properties. So while you're growing potentially feed and food, you might as well also make new packaging materials, new plastics using the same type of protein. So production process of that, how would it look like? Well, you typically have a culture that you grow. The easiest is to use pure cultures, but you can also use mixed cultures. Then you have to lyse the cells and extract your products, such as PHA and the protein. And so I mentioned PHA here. So PHA, polyhydroxyalkanoates, they are actually, at this moment, the most well-known bioplastic that is produced with microorganisms, besides polylactic acid. But PHA is a storage polymer that microorganisms make, and upon extraction, it can be as such used as a polymer, like for agricultural films. And so today, production of PHA is fully oriented towards PHA, which is really a pity. Because you grow microorganisms, you force them in a direction to make a lot of this internal polymer, which has certain yield and growth penalties, and the extraction of the product actually destroys all the rest, like the protein. And so what we are looking into is making a combination of getting both the protein and the PHA from the cells. And so in the very last part, I'm sorry, I'm an engineer, so you're going to see some numbers. I'll tell you why it's attractive to harvest, to aim both for example, protein and PHA as a biopolymer when you do a production process. And I'll give you this example with what happens if we go back to our potato factory and we have a potato wastewater. And that wastewater comes, not all the numbers are important, we have 5,000 cubic meter of wastewater coming out of this plant. Let's say it contains organics, it contains nitrogen, right? And we're gonna grow microorganisms. So let's say we set up a new protein production process, and I only want to do that. Then what you see in this table is that we can grow microorganisms, but there's a lot of organic matter, starch, the like in the wastewater. There's not much nitrogen. So quite quickly, I run out of nitrogen to make more protein, because protein is very nitrogen rich. So if I want to make microbial protein, I'll have to buy nitrogen, close to 700 kilograms a day, that I throw into this wastewater in order to make more protein. So I end up in about 12.5 tons of protein. I can go the other way. I can get companies come in and say, oh, no, we're going to make polyhydroxyalkanoates. We're only going to make this plastic. Well, if you're going to make this bioplastic, what's going to happen is these microorganisms are first going to grow in the wastewater because there's nitrogen there. And once they've grown and they run out of nitrogen, they can't grow anymore. Then they'll use the rest of the organics to store the polymer inside. If you do that, then with a typical stream there, you're only going to have about 40% of the cells containing your bioplastic. But you want 80% in order to have a good production process. So what you have to do, you have to throw in about 25 tons of additional organic matter in order to have more bioplastics, wherever you get it. So whichever route you choose, if you choose one product, you end up with a situation that you have to amend the wastewater, or you end up with a low yield or a low content of product. If you allow, by developing new extraction processes, to harvest both the protein and the plastics, then your story is different. Because the cells grow, the cell accumulate PHA, and you harvest them both. So rather than having about 40% of useful product without amending that available organic stream, you end up with about 82% of useful product. This means that you use the organics from the wastewater at a carbon efficiency of about 82%. It's much higher. It's a different view of how you produce and how you look at your product. It's not just one product, you have to harvest 2 products, which is more complicated, but you use the feedstock much more efficient. So to end, I hope I've been able to convey a bit the message that microbial protein is a product that you can produce from carbon dioxide, carbon monoxide, or the derivatives like ethanol, and from organic side streams. Typically, the cell can contain up to about 70% of protein, which is high, and they have very interesting amino acid compositions that you can use, for example, for aquaculture. Products at this moment are being produced at 50 kilogram level and beyond. There's quite a few companies in Europe now focusing on new forms of microbial protein. In our case, we verified this with salmon and prawns, but you can use the protein also for other applications, such as plastics and packaging material. With that, I'm happy to take any questions you may have. The QR code is a link to a video that was made for this project, where we made from ethanol the protein, but you can also just find it under SEMPA online. Thank you very much.
Thanks, Korneel. Is there any question? Yes, please.
Yeah, you have a microphone.
Thank you. Very interesting, many interesting information. Maybe I missed the first part, because typically you need hydrogen and CO2, right, to have microbial proteins. But you then spoke about the use of alcohol, which
yes.
means you are not using any more gases for feeding the microorganisms. Is that correct?
That's correct. So there's different routes in which you can go to protein, and indeed one route is to use hydrogen and CO2.
Yes.
And there are companies like Solar Foods doing that. The thing is, there's two things that make that difficult, to my opinion. First of all, the hydrogen is very expensive today. You're looking at €8 a kilogram for green hydrogen. And two, you need to do your production in a gas lift type reactor. And so yield-wise, it's not optimal. If you have a different process, like what they have at ArcelorMittal, from the gas, they produce ethanol in a very intensive reactor. There are microorganisms really good at producing ethanol at a high yield. And then if you take that ethanol, that is actually an excellent organic substrate to grow microorganisms in a more classic, a classic aerated reactor. Because, industrial biotechnology, there are gas lift reactors, but they're expensive. It's difficult to work with, while you do have a lot of products you can make from gases or from other substrates like ethanol, like methanol. And these are, to my opinion, much easier to produce a product with. An extra advantage is you have an off-gas, in that case coming from a steel plant, or it can come from some other industry. If you directly produce something in there that you're going to use for feed or food, it's going to be hard to get that approved. But if you produce an ethanol and you do a pre-distillation, you separate away that product from the production reactor, and you can really have a substrate that has a measurable quality, and that will facilitate getting approval for its use as well. So, of course, it's 2 steps versus 1 step. If you directly use hydrogen CO2, you can do things in 1 reactor. If you do it in 2 stages, then you can, it's a bit easier from a technical perspective, but you have 2 stages. I think a last advantage of using organic substrates like this is that there's a lot of them already available. If you're going to make a first production plant on ethanol, you don't have to take all this ethanol coming from gas. You can get it from fermentation, from other sources. There's already a lot of this product around to get you going at the right level of production, right? And then later you can make this greener and greener and greener, but you can already start, right? Which is the challenge on green hydrogen, which is there's no green hydrogen or almost no green hydrogen available. So it's nice to put a production process, but the electrolyzers are not there to produce it. So where are you going to get it?
What about the nitrogen?
Yeah.
What kind of compound or compost do you use to supply nitrogen?
So at this moment we look mainly at the virgin nitrogen, but we have verified that you can use different kinds of recovered nitrogen as well. So we've done tests with ammonium sulfate recovered from side streams, with ammonium hydroxide, ammonium water, ammonium carbonate. So these sources all work. But typically it's an ammonia source, not a nitrate source we use. It's nitrate, you're looking more at phototrophs, algae that use that. But so it can be recovered nitrogen, and it will have to be an economic consideration whether it's worthwhile doing it. Recovered nitrogen is really cheap, but then again, you have a whole approval process. If I take from a manure digester, I strip out the nitrogen and I recover this nitrogen as ammonium sulfate. As an engineer, technically we can say, I can make clean ammonium sulfate, but from a legislative perspective, this is waste. And so to get approval to use that waste in a food or feed product is going to be difficult. That's also where the line of making packaging materials from proteins is more attractive at the moment, to my view. Not for food packaging, but for other packaging purposes. If you can use this protein, you can use recovered ammonia. You don't have to go through this whole legislative route to make a base packaging material or an agricultural foil. You can go much faster with also low-grade side streams. So that's where the application is interesting. The funny thing is that in terms of value, if you grow protein and you sell it for feed or food, it's worth 2-3 euros per kilogram. If you take the same protein and you sell it for a food packaging, it's worth 15 euros a kilogram, same material. You just have to make sure you reach the grades that they desire, but there's a lot of value in packaging materials Not everything we recover from resources needs to go back into agriculture or food. It's a bit of a too singular drive to put everything back into the food chain, while we need a lot of packaging material as well. So it was a bit of a long answer, and I'm in between you and the coffee break. Are there any other questions?
I think we are running late, so we have to move to the next presentation. Thank you, Korneel.
Thank you.
So the next presenter is, yes, is Dimitrios Bikiaris from the Aristotle University of Thessaloniki, expert on biopolymer evaluation and also polymerization.
Hello, good morning to all. Thank you very much, Apostolis, for inviting me to come here in this workshop and to present our works in bio-based monomers and additives for sustainable polymers. Unfortunately, I realized today morning that I have only 15 minutes. I will fasten a little bit out my presentation. So, no. I'm telling always my students that we are in the plastic age. Plastics are ruling our lives. They reply to me that we are in the age of information, internet, TikTok, Facebook, Instagram, probably they have right. And till today, we have about 9.1 billion tons of plastic that have been produced since 1950. About 400 million tons of plastic are produced every year, and as we can see, plastics are everywhere. Most of them in packaging application, 40%, but also in building construction, automotive, agriculture, everywhere. And there are some negative issues on this. We can see also that the plastic production will still rise up in the next years. This causes a lot of problems. The first one is the carbon dioxide emission, and according to the Center of International Environment Law, the total life cycle greenhouse gas emission of plastics will be expected to grow from 0.86 gigatons in 2019 to 2.8 gigatons carbon dioxide in 2050. This is a negative contribution. And as we can see, this causes a lot of problems. Carbon dioxide raises up following the increase of global population. And the good news here is that we expect it next 10-15 years, the maximum level increase of global population. And from 1970, we pass the 0 year, let's say, that after that, carbon dioxide emission is annually growing up. This causes problems, and as we can see in the other slide, we expected in 2010 the average temperature to be increased about 3.8 degrees Celsius. This means that the level of the sea will increase from 1.5 till 3 meters, and the half of the population will be underwater sea level. Will not be here to see it. This is the good news. Also, in the plastic, we have the 3 R rules in plastic life cycle: reduce, replace with other materials. We are going back to paper, wood, glass, metals, even though the plastics have many advantages. Reuse, in some cases, this is very difficult because the plastic life depends on material type and user. Plastic bags are sometimes reused, but in most of the cases, very difficult. Films, bottle, boxes, pipes, and we have also thermosets that is impossible to be reused. Recycle, only 9 to 10% of produced polymers are recycled, 20-30 in Europe, which are the leader in this effort. Another small amount, 12%, is incinerated, and the biggest percentage, about 80%, is discarded and accumulated in the environment. Ocean and lakes cause many environment problems, and the most of it is microplastics. Fragments from dimension lower than 5 micrometers, and In 2016, about 11% of plastic waste was released in aquatic systems. 15 trillion of microplastics are floating at the oceans. This is the estimation, a huge number. And until 2050, the weight of microplastics will exceed the relative weight of fish. This is very difficult to understand. We have done in our lab many works in microplastics, but the negative thing is that microplastics are everywhere in our body. They are in our blood, they are passing our brain, and this is, no one knows what will cause to our health. Next year will be, for sure, this issue will solve. For all this, the strategy of EU that was published in 2022 was changed, and a new strategy announced to contribute to the transition to climate neutrality and zero pollution ambition, and highlights the research and innovation area crucial for making chemicals and materials safe and sustainable. To this direction, biomass probably is the key of all these efforts. It's produced in abundance from plants every year through photosynthesis using only carbon dioxide and water. However, all this chemical energy that is stored in biomass, about 4,500 exajoules, it is 4 times the energy that globally we consume every year, in the form of glucose or sugar, is lost during the annual cycle of seasons. And we can use this biomass to take some monomers, to take some additives, as we will see. The key here is glucose. You can see from glucose we can produce everything, and we can use animal or vegetable biomass. We can produce ethylene, propylene monomers, or for commodity polymers, or other like vegetable oils, furan, terephthalic acid. Also, we can produce materials from monomers from lignin and additives from this biomass. Today, there are plenty of new chemicals, bio-based monomers in the market, diols, ethylene glycol, propanodiol, butanodiol, and isosorbide. We will see isosorbide in the next years, diacids, succinic acid, sebacic acid, terephthalic, itaconic and furan dicarboxylic acid, diamines, hydroxyalkanoates, and furanoates. Trying to solve the problem of carbon dioxide emission, we are going to produce some bio-based monomers. This is an example here, producing ethanol for catalytic dehydration, bioethylene produced from ethanol, and as you can see, the carbon dioxide emission is only 0.00173. In the case of biofuel ethylene produced from naphtha, you can see that it is 1.2 kilograms carbon dioxide per kilo of ethanol. This is a big difference, about 700% that's higher. In the case after producing polyethylene, using bioethylene and ethylene, the production, the carbon dioxide emission is the same. So this is the gain. The carbon dioxide emission is drastically reduced, but do we solve the problem of microplastics? No, because the polyethylene, either produced from naphtha or either produced from ethanol, bioethanol, has the same properties. So we can also have a lot of bio-based nanoadditives, nanocrystalline cellulose, nanolignin, which is the structure with phenyl groups, and biochar is produced the last year as byproducts from production of biofuels. All this can be used to reinforce plastics. In a previous project we have Biomac and finish next month, we try to use ultrasonication treatment to produce nanolignin, because nanolignin was produced till today by acid treatment or neutral treatment. And with ultrasonication, here you can produce with a green way using only water, carbon nanolignin. And as you can see here, starting from sulfa-lignin, we start with about 2,500 micrometers plastic, the particle size, and after some treatment, we can see that was reduced less than 500. And this is these DLS measurements, and with transmission electron microscopy, we can see that we reduce the size in nanometers level. And this was used in comparison with lignin to produce some reinforced PLA nanocomposites. The gain here is that it was a substantial increase in tensile strength. You can see there, starting from about 6 megapascal, we succeed to go after adding 2.5 weight percentage of lignin, about 25 micro plus 5 times higher. And also, it was increased again the Young modulus. Here again, some results from Biomac using nano cellulose for food packaging application, using coating, and also with nano imprinting nanolithography. You can see some interesting columns here that avoiding, as you can see, the growth of microorganisms. In another attempt, we used bio-based succinic acid and butanediol to produce some bio-based polymers, and also to use biochar inside to reinforce this. You can see that we have succeeded to produce high molecular weight polybutylene succinate, but after the addition of biochar, the elongation break reduces slightly. But the positive here result was that biochar, after UV radiation, you have seen that stabilizes polybutylene succinate against UV irradiation. The molecular weight reduction in all reinforcement composites are lower compared to neat polymer. And with another partner, with AIM+, we applied a new technique to produce some copolymers by using ring opening polymerization of PLA, because PLA, we know very well, it is a combustible material, but is not biodegradable. We want to see how to produce biodegradable material, and with this technique, we succeed here with radiative extrusion to produce, as we can see, high molecular weight polyester polylactide in just 15 minutes. To produce in laboratory scale apparatus this molecular weight, you need more than 2 hours, and we succeed to produce it in only just 15 minutes. In the copolymers, as the amount of polypropylene adipate here increases, there is a slight reduction in molecular weight, what was expected, but we succeed to increase the elongation break. PLA breaks with an elongation about 2 to 3%. Here you can see by using 15% of polypropylene adipate, we succeed to get films with more than 120 elongation break. And as I said, we want to see if we can produce biodegradable polymers. You can see here the molecular weight reduction, which is much higher in copolymer. All these materials, the innovations here in Biomac, have been produced with other partners, have given to other partners to produce pods with biochar, mulch films with nanolignin, bio-based materials coated with nanocrystalline cellulose, also for printed electronic, and in some cases for 3D printing. Another interesting monomer, bio-based monomers that we are working in our lab is for anticarboxylic acid. Polyethylene furanoate is an alternative material for the production of polyester, especially for bottles, to replace polyethylene terephthalate, because as you can see here, the carbon dioxide and oxygen permeability in polyethylene furanoate is almost zero compared with polyethylene terephthalate, which solve many problems, especially for the production of multi-layer bottles And you know very well that Europe has banned the production of these multi-rail bottles. And the negative point is that even though it is a bio-based material, it's not biodegradable. Also here, you can see some attempts in our lab in order to produce high glass transition temperature polymers in order to replace polycarbonates, especially using for bottles, water bottles, because you know very well all these polycarbonates are producing using bisphenol as monomer, which is very toxic. Here we have been using isosorbide, and you can see that the glass transition, the copolymer, was increased substantially in all cases, reaching the level of 140, which is very similar to that of polycarbonate. Some other attempts to our lab is to use all these aliphatic acid and other bio-based monomers to produce non-isocyanated polyurethanes. There are many calls to this direction because isocyanate monomers are also very toxic, and there is another gain that for the production of these non-isocyanated polyurethanes, we can use bicarbons, and in each molecule, there are inside 2 carbon dioxide molecules. A PhD, 2 PhDs are running in this area. Also, we are trying, in collaboration with our partner that is also here, in our national funding project, to produce some bio-based epoxide as adhesives and also as coating. There is a big study here in order to produce coating to replace Teflon and other fast materials that use for coatings. And also, some attempts are here to produce from using succinic acid and other diols to produce some acrylate bio-based adhesive for similar application for wood products like particle boards, again with HIMAR. And in all these attempts, we succeed to get funding for a recently project, Greco, that was started in May, using innovative-based biodegradable and recycled semi-circular food packaging materials. And this Greco will start it in May with partners from 30 countries. And as conclusion, let's work to design, synthesize, and produce recycled, bio-based, and biodegradable polymers for a green and a safe world. As polymer scientists, we have a great responsibility for environment and human health protection. And I'm always doing 2 questions. Can we replace all non-degradable polymers with some degradable and bio-based polymers? And the biggest question that is not answered, especially for me, shall we stop polymer production in order to solve all these problems? Thank you very much for your attention.
Thank you very much for the great presentation. So, is there any question?
Yes, thank you. It's very beautiful research. So it's very close to conventional research. And only last question, should we stop polymer production? And from my point of view, it's not the solution. And polymer is very crucial material in the life, in our daily life. So I will also present a little bit more from a conventional point of view and how to make it better. So not to stop, but make the polymer better, and which you don't need to recycle. Thank you.
Okay, thank you very much. And the solution of all problems for me, because we are working since 2000 when I was elected as professor in Aristotle University, is trying to solve all these problems with new materials, bio-based materials, because nature is creating some monomers without to give something, without to pay something. Glucose is the key monomer for all this, the production, but always I'm saying, okay, we can produce bio-based polymers. Bio-based, almost 30% today of production of polyethylene is from bio-based ethylene, but it still has the same problems for environmental pollution. So the key is not to stop for me the production of polymers, but to produce new polymers with, which will be recycled and also will be degradable, because as we have seen, it's very difficult to recycle all polymers. I was in Egypt 1 year ago, and you have seen the river, the Nile River, full for floating polymers, polyethylenes, bags, bottles, foams, everything. All these are ended to Mediterranean. So it is not worthy here to make some efforts, the other Mediterranean countries, Italy, Spain, to reduce the pollution, to recycle polymers, and some other countries not to take action about this. It's a very difficult problem. That's why I'm saying that the solution could be the production of recycled and biodegradable, fully biodegradable materials. Even in the case that these cannot be recycled, when they are into the environment, will be degradable and not harmful for the environment and our health.
Okay, so if there is no any question, let's make a small coffee break for about, let's say, 20 minutes. So let's have a break till 11:20. Thank you very much.
I would like to start the second part of the workshop, starting with the presentation of Emeritus Professor Demetres Briassoulis from the Agricultural University of Athens.
Okay. We'll talk about the challenges for bio-based, biodegradable in soil emulsion films, and for bio-based packaging, mostly compostable. The use of agricultural plastics is expanding over the last decades, and the reason is the multiple benefits offered for the farmers towards a sustainable agriculture. However, recently, questions are raised. Are agricultural plastics a threat? What kind of threat? We know the last decades, because of the expanded use of agricultural plastics, that the management of agricultural plastic waste is a very difficult to tackle problem. Why? Because we're talking in several categories of agricultural plastics about very big volumes. It's not a waste that you have the bottle and you throw it in the bin. The result of the problem of agricultural plastic waste is that they are mismanaged mostly and all over the world, including Europe, in various ways, including discarding in the fields, burying or totiling the plastic remains into the soil along with the plant remains, or burning them uncontrollably in the fields. What does this mean? Discarding them means aesthetic pollution, landscape degradation. You may have seen also examples, unfortunately, also here in the beautiful island of Crete. Threat to animals, blocking of water channels, overload and extra cost for landfilling for the municipalities. Burying in the fields means irreversible soil contamination with degradation of soil characteristics and possible risks for the food safety. Burning in the fields I think all of you can imagine what the problem is, burning plastics and having toxic substances released like dioxins and others in the environment, a problem, a high risk for health, and also high risk possibly for the food. All these mismanagement practices are forbidden by the European and the national legislation. However, they continue. Why? Because the farmers have no solution. What are they going to do with these huge volumes of, for example, greenhouse films? How to manage them? This is a problem of the European legislation that has not dedicated specific threat, a specific waste stream for this category of agricultural plastic waste. Going to the mulching film is a specific category of agricultural plastics. And this category, I think all of you know what mulching films are. After the end of their useful lifetime, they are already degraded and contaminated and difficult in terms of labor to collect. And there is no option for material recovery. They are not considered recyclable for technical reasons and also in terms of cost. So what is the solution? The alternative solution is that they're collected at a high labor cost because along the longitudinal edges they're buried in the soil. It's very difficult to take them out of the dry soil. And then in order to root them for incineration, for energy recovery, you need to go through a company that will convert them into alternative solid fuel, and the whole process is of high cost, and nobody will do that. Now, coming back to the threat, is this the threat? That was one problem, but the threat is a different one. It has been, it appears in many reports and publications very recently. What is this? Agricultural plastics are considered now as responsible for soil pollution by micro and nanoplastics. A lot of attention has been paid the last decades on the contamination of the oceans by microplastics, but not for soil. A recent report by FAO suggests that plastics in soil threaten food security, health, and environment. In a recent publication, going through a systematic literature review of publications about the abundance of microplastics in soil, the results are very interesting. You see here, I don't know how clearly you can see, in the first figure, you see the wide range of abundance values of microplastics in terms of number of microplastics per kilogram of dry soil. And you see numbers reaching up to 10,000 particles of microplastics. Microplastics are defined, as we have seen before, as small fragments less than 5 millimeters of non-degradable fossil-based or perhaps bio-based plastics non-biodegraded in soil. This is the definition of microplastics. Biodegradable particles in the soil are not defined as microplastics, even if they are less than 5 millimeters. We see here, most of these reports come from China. Why from China? While the classical, the conventional emulsion films are 15 to 20, 25 microns thick, in China, over the last 30 years, until recently, they used very thin films, 80 microns, 5 microns films. And of course, they could not collect them, they left behind. And what they did, 20 million tons of plastic emulsion films over the last 30 years left behind 2 million tons of plastic residues in soil. And this is why you see very large numbers from many regions of China, but also even from Spain and other regions in Europe and India and other places. At the small amounts of abundance, you can see 500, 1,000 particles per kilogram. If we go to this pollution is called white pollution. If we go to see the composition of these microplastics, based on this literature review, we can see acrylic, polyamide, rayon, polyester, polymers that are not used with agricultural plastics. Along with polymers coming from emulsion films and agricultural plastics. This means that we have multiple additional to agricultural plastic sources of soil pollution by microplastics. Which are the sources? Biosolids, treated wastewater, compost, a serious source of microplastics. Also, domestic sources, industrial sources. You can see that these microplastics find their way to soil through compost, through biosolids, etc., from specific applications. One major application is cosmetics. Microplastics are used intentionally in the cosmetics industry. Also from textiles. We will see this in the next slide. When we look at the form of microplastics in soil, a major category is microfibers. And these microfibers probably come mainly from textiles, also domestic uses, biosolids. These are the ways that they come into the soil. Microfibers made of polypropylene come from agricultural plastics. Those of polyester, rayon, etc., come from textiles. Then we have fragments from PVC, high-density polyethylene, polyesters, from packaging films, bags, containers. And then we have polyethylene films, the form of films in microplastics, which come both from agricultural plastics like emulsion films, but also from packaging. And we have seen a lot of remains of packaging in agricultural soils, which have found this place through runoff, through wind, through mismanagement in general of packaging. So we know, we have seen before, that recycling is low, even in Europe. So this is a way of pollution of soil by microplastics. Then a solution to the problem could be biodegradable in soil, bio-based emulsion films. This is based on selected bio-based polymers, which can be certified as biodegradable in soil. And as you know, not all bio-based polymers are biodegradable in soil. These bio-based biodegradable in soil emulsion films can be incorporated in the soil after the end of the useful lifetime, eliminate the environmental and food safety problem, and there is no need to collect them, eliminate the management cost. So even if their price is higher than the conventional polyethylene-based emulsion film, if you consider the cost of the management of this film at the end of the useful lifetime, perhaps the price, the total cost is lower. But so far, the farmers, the polluters pays principle is not applied. So the farmers consider cheaper the conventional emulsion films. This is a problem of the implementation of the legislation and the lack of infrastructure. Biodegradable in soil emulsion films, certified according to European norm 17033, everything fine during the useful lifetime, and at the end, they are rototilled, let's say at the topsoil, 10 centimeters thick, and we have a dispersion of the macro fragments of this film, the degraded film, into the soil at a low concentration, depending on the soil class, from 0.18 to 0.12% dry weight. Then, after the incorporation, biodegradation starts, if they are really biodegradable in soil. And then we have a combination of biodegradation and abiotic degradation in the soil. And we have these microparticles, not microplastics, biodegradable in soil, of diminishing gradually with time size and diminishing concentration in the soil until the end of full biodegradation in the soil. Here you see the results of an experiment, a recent experiment in the experimental field of the Agricultural University of Athens. You see the disintegration rate in the field during of a film incorporated in the soil during summer and during winter. And, the result shows disintegration, full disintegration within a period of 5 to 7 months under irrigated conditions. It's interesting to compare these results against the results of another project 20 years ago in the same experimental field, made of similar but not the same grade of starch-based emulsion film with lower bio-based content at that time, different grade, but we have similar results. You see here a comparison of a PHA-based emulsion film with PLA film after 30 microns thick, after 4 months of exposure. Here you see the PHA-based film in 1 to 3 months of exposure in the soil, and the corresponding picture of PLA film after 7 months of exposure, which is not biodegradable in soil. Biodegradation is measured in the laboratory using the provisions of international standard test methods like ISO 17556. You see here with the blue and green line the positive reference materials, PHBK, and cellulose, and the purple curves show the emulsion film we saw before for disintegration in the field, following artificial aging in the laboratory. Why we did that? Because we simulated the natural degradation of the film in the field exposed to the sun UV radiation. And without artificial aging is the lowest curve, which shows slower initial rate of biodegradation. Within a period of 1.5 years, this film is biodegraded. The standard specification requires more than 90% biodegradation within a period of 2 years. Which are the challenges now for these materials? First, increasing the bio-based content. Then investigate alternative raw materials as a source for the production of these bio-based in soil polymers, preferably from bio-waste and byproducts of the agri-food industry, and also, like we're doing here, the bio-waste part of the municipal bio-waste collected in the special bins for compostable materials. Reducing the cost of the new bio-based biodegradable soil materials, then improve the performance of these materials. How? Making films thinner. For example, now the most of biodegradable soil mulching films are 15 micron thick, thinner than conventional, so a lower mass is used for these films. The durability during the useful lifetime with a good stabilization scheme. And labeling. There is a big problem in the market, even in the scientific community, with the term biodegradable. This is biodegradable. PLA is biodegradable. I use PLA for mulching films. No, it's not biodegradable in soil. There is a confusion with the term biodegradation. There is no material biodegradable, full stop. No, there are materials certified as biodegradable in specific environments. And this confusion has, of course, is of course a reason of doubts for many farmers or the suppliers, even the industry producing these materials. I don't know if they will really biodegrade in soil. They don't understand labeling, certification, or in some cases we have misleading information in the market. This is a big challenge. So this is also a matter of the corresponding legislation at the European level to tackle this problem. Now, a short presentation about bio-based compostable packaging. Here again, the preferable use of bioproducts or waste of the agri-food industry is as the main raw material for the production of these materials. The aim, among other aims, is the elimination of micro nanoparticles in compost. Materials which are compostable should be really compostable in the industrial facilities of aerobic composting. The corresponding claim for biodegradable in soil forms and films. The question is about the presence of microparticles, macrofragments of packaging films which are compostable, but they are not biodegradable in soil and find their way to the soil through the compost, no if they are compostable, but through the biosolids, compostable plastics, food packaging plastics, compostable and not biodegradable in soil, will and may end up polluting the soil with microplastics, biosolids, wastewater treated, wind, runoff. Ideally, food packaging, bio-based, should be both compostable and biodegradable in soil, unless there are very strict regulations about this product. So far, let's say, for biosolids, EPA in the United States and the corresponding legislation in Europe have paid attention to chemicals, heavy metals, pathogens. Nothing about microplastics. And this is a big problem. An additional benefit of bio-based materials used for food packaging are their physical characteristics, which allow for prolonged self-time for horticultural produce, fruits, vegetables. This is a big advantage, and not many people know about that. I conclude with the results of two recent research projects we carried out with the group of Apostolis. Utilization of flower industry byproducts to produce bio-based biodegradable active food packaging, and utilization of agricultural residues from sugar beet cultivation and byproducts of the sugar production process to produce bio-based compostable packaging. Thank you.
I would like to thank Professor Briassoulis for the presentation. I would like to ask the audience if there is any question. Yes, please, Robin.
Thank you. It's a very interesting topic, but I feel it's kind of a dilemma. We have a growing population, we need more food. More food, you need agriculture. So in order to have more food, you need production. So this agriculture, film, whatever, at the end up in an environment which is not desired, but this is a consequence. And the population is growing. Now we are facing an issue, and a company like Corvette, like other companies, we are investing and how to convert this waste into chemicals, because that's become fully circular. Now we are moving linear. You make a production and you end up in the environment. It's not the desired. So maybe that is a future we have to target for, because just to reduce the production of the food is not the way to go, because the population is growing every day. That's my comment.
Thank you.
Thank you very much for the presentation. I mean, today, the numbers of biopolymers which are biodegradable in soil are very, very few. I mean, PHA, PHB, maybe one copolyester, and starch, you know, all these natural-based materials. So my question is this: do you think that we should go also to other kind of films? For example, there is a work on some colleagues from Napoli who have also made a patent on the possibility of using spray coating directly on the soil based on a combination of different natural polymers and natural fibers. But it's a totally different approach compared to the films, the typical plastic films. Do you think that this, let's say, alternative approach could be a possible solution, because you have many more possibilities?
There are publications about that from a group of CNR in Naples, led by late Mario, you know. Yes, we know. This is, has been tested also recently by the same group. There are some positive outcomes, but it's not a standard film, as you understand, because the soil is not a flat surface. And there are various activities from animals, from farmers, and so on. I don't know. It could be an alternative under certain conditions, if it can be controlled, for example, under greenhouse conditions, hydroponics, etc. But in the open field, I think it's very difficult.
Thank you very much, Professor Briassoulis. I think we can conclude the presentation. We can move to the next speaker. I would like to welcome Rubin Huang from Covestro to present us the experience of bio-based materials in sustainable coatings.
Okay, thank you. Good morning. My name is Rubin from Covestro, Holland. Firstly, I would like to thank the organizing committee for inviting me for a talk. And also, I was really impressed by this city. It's a really beautiful city here. And also, a lot of people online. I hope you are not really jealous about us. We are on set. So today, I'm going to talk about the bio-based materials for sustainable coatings. Maybe some part is beyond the coatings. So for today, the presentation, I will cover several topics. First, I want to talk a little bit about the Covestro, who we are, what we are doing, and also I will touch a little bit about the circular economy. It's becoming more and more important, and also focus on the biomass as a raw material, and also bio-based products in use. And also last is the bio-based research and development, especially in these EU funding projects. And at the end, I would love to answer any questions you have. Covestro, and maybe for most of people it's not known, but Covestro is one of the inventor and the leader in the high-tech material solutions. So we are #1 in the world for polyurethanes in the material and also relevant products. And for sure in the polycarbonate business, it's the world #1 at the moment. So Covestro is one of the biggest polymer producer. And company has such a big size, so we have a really strong purpose and also very clear vision. So we want to make the place of the earth a better place to live. And we want to become fully circular. So we hope our company will become inspiration for other companies to follow and also to solve the current problem. And a lot of challenge has already been presented. So that is the company is working on for the solution. Covestro is structured in 2 segments. So we have performance material. We also have a solution and specialties. And I'm working in a business unit of coatings and adhesives. That will be the focus of today's talk. Yeah, circular economy is becoming more and more important, as I mentioned also in the QA's part, and it become the company guiding principle. Because that is the global challenge. A lot of people already present. So we have a climate change. We have the disruptive, the ecosystem, growing population. So you cannot ignore that all the factors will influence the way of working, the way of thinking. So it's a global challenge, and we need to take action. And in principle, action should be taken now. Why is the circular economy? Because we used to be the linear. We produce, we consume, we waste, we end up in the environment at the end, and we are lacking resource. So we have to change the way and how we operate from production as a consumer, our consumption, and also if possible, bottom line, we have to avoid, minimize the waste, because waste is everywhere, not only on plastics and also food waste. That is really a lot to be handled. Yeah, for Covestro, and we have a clear vision, and for the vision you need action, otherwise it will become a slogan. And we, as a Covestro, we have 4 pillars in order to realize the circular economy. I will not cover all, and today I will focus with alternative raw materials, for example, from biomass, from carbon dioxide, and also end-of-life products. Yeah, in fact, Covestro products is everywhere. It's already contributing to the environment, especially the sustainability. As I mentioned, Covestro is the world #1 polyurethane raw material producer. So polyurethane is not new. And in the construction, you need a polyurethane foam for the insulation, and which will help for the building, which is energy efficient, and also with this already help in the sustainability. Engineering plastics, we talk about polycarbonate. It's already make the auto ladder, and also to enable Now it's a very, electrical is everywhere, electric car, electric mobility, and you need high-end polymers in order to make it happen. And also in the solution and specialties, and we are moving away from the solvent-based coatings. At home, maybe still experience the coatings still have a solvent, have a strong smell. And also we are moving away, now we replace by water-based. And also we are exploring the bio-based materials in order to improve the CO2 footprint. As a Covestro, as all other companies, in order to remain competitive, you need to minimize the investment. Otherwise, as a company as such, and you cannot really compete with other traditional company. So we are looking for and also striving for any alternative feedstock which can be dropped in or nearly dropped in. For example, the bio-based succinic acid, and from LUCRA projects, and when the purity is high enough, it's almost like drop in. So for us, we can directly use in our current plant without the investment. Circular, and also we'll talk a little bit the climate neutrality. So that is the 4 different routes. I think we talked about already some other speakers. So you need to handle the way to make it more circular, to catch all the carbons. So I will not talk about all the 4 elements, and I will focus on the alternative raw materials. Not only Covestro, but our customer as well, they are looking for and also asking support from Covestro how to reduce the scope 3 emissions. Maybe you are not really familiar with the scope emissions, because that's from the United Nations. So they have a scope 1, 2, and 3. And scope 3 is really about the products. So how you can change your products in a way which can reduce the greenhouse gas emissions. In Covestro, we are exploring to use different raw materials, bio-based, recycled material, and with a certain percentage of this kind of raw material, we have the CQ label. We call it the circular intelligence. And based on the RCA, our products with the CQ label has a less environmental impact. So that's why we are promoting these kind of products more and more to the market, to our customer, in order to reduce the environmental impact. Yeah, why we are talking about the biomass, and this is also the theme of this conference, this workshop. Yeah, because fossil is limited, and one day everything will be gone, and it takes centuries in order to convert and to the new fossil. And also they will reduce CO2. And bio-based raw material is the opposite. So they are renewable, they are CO2 neutral. So that's why this become our hot topic. And also in Covestro, we're already exploring, together with other partners, other different research institutes, we are talking about to make new polymers, new monomers from plant-based, from sawdust, like LUCRA, and from PACO as well. So it's a municipal solid waste, and how to convert and how to get this building block instead from the oil from a fossil and from other renewable resource. So as also other presenters already say, the plastics, the bio-based plastics only 1%, and we are expecting will grow this market 3% a year. Yeah, so this bio-based products already in use. It's not new, and Covestro already promoting a lot in the market and using bio-based content, bio-based raw materials. For example, the high-ending, your automotive, your car coating, furnitures, floor, and also your textile, your clothing, your shoes, and even the phone that you are playing with. It's all some already containing the bio-based or is recycled plastics. Last but not the least, Covestro alone cannot reach the target for the new technology. So we are cooperating with different partners. Like now we have a PACO and the LUCRA projects, and for the EU funding projects to try to explore the different way to get the materials, building blocks for Covestro. So we are involved in the past PACO, and this now is followed by LUCRA. In the past, we also have a smart box and the BioCAD polymers. This is just high level, I think probably already, most people already know. So this is a PACO projects, and the Covestro was already part of the projects. and trying to explore the application of this raw material from these projects. Also, Smart Box, at that moment, is already exploring the lignin and also cellulose from the wood, and it's also European-funded projects. And as a Covestro, we are trying to see if we can incorporate this monomer into high-end polycarbonate. Last but not least, the BioCat polymers is exploring the sawdust or wood chips, and also to making different polymers. And for example, making polyurethane or POD dispersions. Yeah, so this Covestro, as I explained, and we want to become fully circular, and with all these ways, and hopefully we'll reach our target, the detail escape. So that's all for my part. Any questions for me?
I would like to thank Robin for the inspiring presentation. Is there any questions?
No, it's very clear. Okay, thank you.
Okay, so Reverend, I would like to thank you. We will have time to answer questions during the panel discussion. Okay, so we can move to the next presenter, which is not Dimitris?
Good afternoon. Thank you very much for the nice invitation for this workshop. All lectures are very interesting. I am Konstantina Karydi. I am the R&D manager in our company, HIMAR. And my presentation today has the title Proteins as Feedstock for Bio-based Wood Adhesives as a promising alternative to our adhesives, to fossil-based adhesives, our conventional adhesives. Thus, today, I'm going to present you our activities as an R&D company, our green technology, some information about funded projects of our company, national and European funded projects, some photos of our R&D facilities, and finally, some projects that we are involved in. And at the end, some closing remarks. HIMAR is an R&D company with expertise in adhesives and additives for the wood-based industry. We also offer technical support and training services for adhesive and panel manufacturers. We offer R&D services for third parties, and we participate in various national and European projects. Also, we offer some specialty services concerning the production of chemicals and accelerators or hardeners. We are the representatives of some equipment, of 2 equipment companies in Greece and Cyprus, and our laboratory is accredited for the determination of formaldehyde, the emissions and the content of formaldehyde. We also offer testing and evaluation of resins, additives, and also boards. Thus, our technology for adhesives includes the amino and phenolic resins, like urea formaldehyde, urea melamine formaldehyde, phenolics, bio-based resins, and also no-added formaldehyde binders. All these adhesives are used for the production of wood-based panels, like MDF is the fiber board, particle board, OSB. OSB is the oriented stranded board, plywood, laminates, engineered wood like glulam, LVL, and CLT, and also insulation materials. HIMAR, starting many years ago, has also some green technologies. HIMAR develops many bioadhesives. We have used and we are using a variety of materials derived after extractions or specific treatments of biomass or waste streams. Some of them are lignin, tannin, cellulose, saccharides, proteins, bioacid, bioalcohols, and many others. We have used these materials in our systems in urea formaldehyde systems, in phenolic resins, in no-added formaldehyde adhesives as additives. We also developed novel composites covering materials and insulation products. We are very active in European and national funded projects. So far, we have participated in more than 80. We cooperate with industrial partners, SMEs, universities, various laboratories all around Greece and also Europe and beyond. We are also a member of the Biobased Industries Consortium. We are a big member. Thus, we can say that we are pioneering in the development of bio-based adhesive systems using various raw materials from renewable feedstocks like lignin, tannin, sugars, starch, and many others. We develop biocomposite panels using non-wood materials like straw, husk, chips, and fibers from recycled wood, biochar, and many others. We usually apply novel polymers for the production of composite wood products and their coatings, and some of them are biopolymers, polyesters, polyurethanes, and also fire retardants and many other additives. Here are some photos of our laboratories. You can see the chemical synthesis laboratory with our equipment, with many reactors. We have a pilot plan for chemical synthesis with a capacity of 50 liters. And we also analyze with various methods, physicochemical, spectrochemical techniques, all of our products. Here, in these pictures, you see the DSC measurements, the DSC instruments, also the GPC and HPLC, and the Kendall method for the determination of nitrogen. In this slide, you can see the board-making pilot plan. You can see the mixtures for the fiber board or the particle board production, and also our cold and hot press. After the production of the boards, we analyze the mechanical properties and also the emissions and the content of formaldehyde with the gas analysis and the perforator method. And now I'm going to present you some projects that we are participating, utilizing proteins. The first one is the project Brew2Bio. This is a project, a national project, that ended on September 2023. The aim of this project was the valorization of organic fraction of municipal solid waste from coffee grounds and orange peel after the extraction of the orange juice. And in this project, we developed many products like sugars, proteins, pectins, limonene, and also lipids derived from coffee grounds and employed for the enzymatic production of biolubricants. Our role in this project was to incorporate proteins and pectins in our systems, and especially in phenolic resins. We used proteins as substitute of our phenolic resins and the production of plywood. Here you can see some results. We have used protein from coffee grounds. We tried many percentages of substitution of phenol in our system. And here you can see the results of a resin where phenol was 40% substitute from protein. As you can see, the shear strength values after the soaking and the cyclic test are very satisfying. We reached almost 1.63 and 1.5 after the cyclic test. These values are quite near with the reference resin, a phenolic resin. In this case, we didn't have good values for the wood failure, But even this, the shear strength values are so good that there is no need for wood failure high values. These values satisfy the prevailing European standards. The next project is the project called Brilliant. It's an ongoing project. It's an Horizon Innovation Action project that ends on May 2027, and the title is Cooperative Business Models for Bio-based Chains in Rural Areas. In this project, we validate 10 bio-based value chains, starting from cardu, safflower and sunflower, potato and rapeseed as raw materials, and we develop many other high-value added bioproducts, like biopolymers, biolubricants, proteins, bioadhesives, and many other products for animal feed or for the cosmetic sector. Our role here is the validation of bioproteins as a phenol substitute for the production of plywood boards. And here are some results where we succeeded to use the rapeseed protein derived from the hot press process of the rapeseed cake, which is the residue after the extraction of rapeseed oil, at a percentage of 50%. This is a quite high percentage of phenol substitute. As you can see, we have very good values of the shear strength after the soaking and cyclic test, and even better than the reference resin, and quite good wood failure values. The next one is the project Disintrace that is also ongoing with a title A Digital Value Chain Integration Traceability Framework for Process Industries for Circularity and Low Emissions by Waste Reduction and Use of Secondary Raw Materials. It is an Horizon Innovation Action, and this project ends at December 2026. Within this project, digitalization with dynamic digital product passports will be performed to optimize secondary materials, cut waste, and enable circular low-emission value chains. Also, AI-guided utilization of wood residues in particle boards will be performed, replacing the virgin wood. A demonstration of 4 pilots will be done for pulp, paper, chemicals, and plastics. Our role here is to use some biomass proteins as phenol substitute for plywood boards, and also to use recycled wood chips in particle board production. Here are some results where we have used proteins from sunflower and rapeseed. We produced the resins with various substitution levels, and then we continued with the plywood production. As you can see, in most cases, we have better wood shear strength values than the reference resins and quite good wood failure values. The next one is a new project, the CERC landfill. Many details were presented by Professor Koutinas, thus I'm going to mention also our role here, where we again use proteins from the organic fraction and for phenol adhesives, and again the production of plywood. As closing remarks, we can say that proteins derived from agricultural and municipal waste biomass are suitable substitutes of the phenol for our bio-based resins, applicable for the production of plywood panels. The properties of these produced panels satisfy the prevailing European standards, and also it was proved that we can use proteins, it is easy to handle these proteins, and without any changes in the processes that we need for the resin synthesis and the board production. This makes very interesting and very attractive the whole process for the manufacturers, because they have difficulties to change equipment and also things in their industrial plants. At the end, we can say that proteins derived from agricultural and municipal waste biomass satisfy the industry needs for renewable bio-derived feedstocks and sustainability. Thank you very much. This is our contact.
I would like to thank Ms. Konstantina Karydi for the inspiring presentation of HIMAR's market interests and recent development activities. Are there any questions from the audience? Yes, please.
Thank you. Thank you very much for the presentation. I'm just curious to know which kind of extraction method you used for the proteins, to extract proteins from these wastes.
We are using the protein samples as received from our partners. We are a laboratory that produces boards and produce bioadhesives. Thus, we don't make the first step, the extraction of the proteins from biomass or waste streams.
Okay. But do you know how they extract the protein?
Maybe they, in some cases they use thermal, hydrothermal, chemical processes, depending on the project. But we are not actually doing this in our activities. We don't have it in our activities.
Okay, thank you.
Can I reply to this question a bit? From vegetable proteins, like rapes, for instance, you can separate the proteins by increasing the pH to 10.5 by sodium hydroxide at the beginning to solubilize the protein, and then precipitation to increase the protein content at the azeoelectric point. This is a conventional method that is used. In case, it depends also on the protein structure. You can also use other methods like solvent extraction or salt extraction to separate the proteins depending on the origin.
Hi, that's very interesting. I have a curiosity, like, can you share more or less what the value or the cost of a protein can be to be used in this kind of applications? And do you expect a lot of differences between different proteins or different sources for your product?
Yes, we expect different prices depending on the method that is going to be used for the extraction of processes. For sure, our sector needs a very active, but also the cost is very important, and also the availability. This is the most important parameters for our sector, the price and the availability. Yeah. Now, concerning the cost, for sure, it has to be lower than our fossil-based components. But I don't know exactly the prices that now cost the proteins that I have presented.
Okay.
In some cases, we do an LCA analysis, but I don't remember, I don't know if Eleftheria knows here about the prices.
We normally compare the prices of the proteins with the conventional chemicals like phenol. Phenol fluctuates according to the price of oil. It's currently over 1,000 euro per ton. But this industry that we are addressing is a mature industry, and the products are cost sensitive. Over the years and with the experiments that we have done, we have seen that the protein route is feasible. And again, as my colleague said, it depends on availability, if it is available at the quantities that are required. We have used many types of proteins from plants, from trees, canola tree, soy protein, also other materials that are not presented here. And we believe it's a promising material for this field.
I may give you some microbial protein if you want.
Yes, of course.
Yes, of course.
Of course.
Okay, I would like to thank
you very much
Karydi for the presentation. We can move now to the next one by Dr. Dimitrios Ladakis from the National University of Athens on sustainability assessment of bio-based succinic acid production.
Hello to everyone. My name is Dimitrios Bikiaris. I'm an assistant professor in National University of Athens. So today we'll present you environmental and economic evaluation for the production of bio-based succinic acid utilizing municipal solid waste, and also some environmental and economic results from production of some polymers and some polyurethanes that they use as a raw material, the succinic acid. So, starting with municipal solid waste, this is the material that you can find in many countries in the world. So, in the European Union, the management of this material mainly managed with a landfill in approximately 23% of this material. For the material recycling, 30%. Composting 19%, and incineration close to 26%. So, European Union in 2021 amounted into 530 kilos of municipal waste per capita. And the organic fraction of this material, which is the part of municipal waste that we need to evaluate, it depends on the country, it's amounting between of 20 or 80% of municipal solid waste. So the composition of this material is rich in carbohydrate content. So this composition makes this material suitable for a sustainable production via fermentation of different bio-based products. In our case, we focus in the production of bio-based succinic acid, which is the succinic acid is a platform chemical that can be found in numerous of applications in food industry, pharmaceutical industry, cosmetics, and general in chemical industry. So some of these applications will be the production of polybutyl succinate, which is a biopolymer, resins, coatings, polyurethanes, and other materials. So the global market in 2021 is amounting between of 16,000 and 30,000 tons per year, and the current market price it's estimated into $2,940 per ton. So, how this material produced, which is the process? The conventional process, the main process that mainly used, start with sterilization of fermentative broth, which is a raw material that used for growth of bacterial or yeast. It depends on the microorganisms that used in different cases. So, in the case of the fermentation, we have the growth of microorganisms and also the production, the bioproduction of succinic acid. In this stage, we used sodium hydroxide as a material that can be controlled the pH, because the succinic acid is an organic acid, and reduce the pH in the level that microorganisms doesn't can growth. So we use sodium hydroxide in the conventional way to control the pH, and then follows the step of separation of microorganisms and using centrifugation process, and the remaining liquid, which inside is dissolve the succinic acid, which create in form of salt with sodium, goes in the columns of resins. So in the columns of resin, the sodium and the succinic acid, the salt of sodium and succinic acid, the succinate, break into succinic acid by anion exchange resigns, where anion exchange resigns observe the sodium, and the liquid rich in succinic acid goes to the next step, which is the step of evaporation, which here the material, the liquid concentrated and increase the concentration of succinic acid. Then follows the step of crystallization. So here we have 2 or 3 crystallizations in order to clean enough the material, which the purity depends on the final application that we need. So, in this conventional way, in this conventional process, in the case that we use ion exchange resins, it is the step that need harmful chemicals like hydrochloric acid or sulfuric acid in order to regenerate these resins. So a more sustainable way which propose for the reduce these chemicals and also increase the overall productivity and yield of the process. So in this case, it's proposed to use electrochemical cell. So with this system, utilize electricity energy that can be found by renewable resources in order to separate succinic acid and simultaneously break the salt of succinic acid with sodium hydroxide. So this process also have the ability to control the pH in the reactor. So we have also the reduction of sodium hydroxide that's used in the fermentation step. In this presentation, we evaluate the sustainability of this system in comparison with the conventional one by utilizing organic fraction of municipal solid waste. So the total process now starts with pretreatment of organic fraction of municipal solid waste. So the first step is the mixing of and sterilization of organic fraction of municipal solid waste, and then goes to solid state fermentation of specific fungus that in this step produce crude enzymes that has the ability to hydrolyze more the structure of organic fraction of municipal solid waste in order to produce a rich in sugar hydrolysate for the further utilization in fermentation step. So follow the step of hydrolysis, which mixed a fresh organic fraction of municipal solid waste with a crude enzymes that produce in solid state fermentation. And we produce the hydrolysate, which concentrated in the evaporator in order to have a more stable material for the further application. So then follow the production of succinic acid, which is the process that I described before, which we also have the new one process, which substitutes the column with resins by using electrochemical cell. So the economic results. So we have estimated the cost of manufacturing and fixed capital investment by taking into consideration different capacities, production capacities. So with this way, we realized that 50 kilotons per year of production of succinic acid indicated is the optimum plant capacity for the production of this material. After of these capacities, the cost be stable, as you can see here. And in comparison between of case one, which is a case with electrochemical cell with a conventional bioprocess, we estimate the cost of manufacturing and the minimum selling price by taking into consideration two different scenarios. The one scenario is the scenario which didn't take into consideration the revenues that could be take from the management of organic fraction of municipal solid waste, and another case is estimated by using as a management price of $35 per ton of organic fraction of municipal solid waste. So, starting with the numbers, the minimum selling price, as estimated from the first scenario, from the case of electrochemical cells, estimated to $3.51 per kilo. And in the case of the conventional one, it's $3.6 per kilo. And in this, the second case, you can see here we have minimum selling price into $2.7 per kilo in the case of electrochemical cell and $2.64 per kilo in the case of conventional one. So here it is in the second scenario, which we have revenues from utilization of organic fraction of municipal solid waste, which is the price is $35 per ton of municipal solid waste, which is managed. You can observe that the second scenario, the second case, which is the conventional waste, is cheaper than the case that we use electrochemical cells. That becomes because the yield in the first case, in the case of electrochemical cells, is better, so we use less organic fraction of municipal solid waste. That means we have more revenues in the second case because we utilize more organic fraction. So this is not fair comparison. So we make another comparison, which we use a standard amount of organic fraction of municipal solid waste into 1,153 kilotons of municipal solid waste per year, which is the amount that's needed for the production of 50,000 tons per year in the case of electrochemical cells. And here we compare with a conventional way, which produce with the same amount of organic fraction approximately 43,000 of succinic acid. In this case, the minimum selling price was estimated into 2.7, as I said before, for succinic acid in 50,000 tons of case 1, and into $2.54 per kilo in the case of conventional bioprocess. So, for the sustainability assessment now, we use as a functional unit 1 kilo of succinic acid. The system that we make the analysis Gradle to Gate. The methodology that we use is CML, and we present the global warming potential, abiotic depletion of fossil, acidification, eutrophication, and human toxicity as environmental indicators. So also here we have the two different cases, and also we estimate these indicators by using electricity from grid and electricity from renewable resources. As you can see, in all the cases, when we use electrochemical cells, indicates lower environmental impact, and this gap, this difference, is increased when we use renewable resources. To continue, we estimate the sustainability for the production of polybutylene succinate by using bio-based succinic acid. The polybutylene succinate is a biopolymer, bio-based and biodegradable biopolymer, which has some mechanical properties which is close to petroleum-derived polymers. So this material, in order to produce the material, we have to combine 1.4 butanediol and succinic acid. This application finds a numerous of this material can be found in numerous of applications in the different sectors like food packaging, matching films, tissue engineering, and other applications. So, for this sustainability analysis, we have the production of succinic acid as I described before, and also we have the fermentative production of 1.4 butanediol by utilizing different raw materials. Here in this analysis we use sugars, glucose sugar from sugar beet, corn stover as a byproduct, and organic fraction of municipal solid waste. So, starting by fixed capital investment, we can see here that the pure glucose has the lower fixed capital investment because the glucose doesn't need it to pre-treat it before goes to fermentation, so we need less units, or that means less fixed capital investment for the production. In the case of cost of manufacturing, we have the corn stover similar prices with pure glucose, because in this case we have another revenues or another save energy things, because the corn stover remaining after the hydrolysis, the solid remaining after the hydrolysis of corn stover can be used for energy production. So this energy goes back to the process and reduce the energy requirements, and that means reduction of the cost of manufacturing. And finally, we have the minimum selling price, which here the lowest minimum selling price indicated when we use organic fraction of municipal solid waste, because we have also the revenues for the management of this material. Now we estimate we use the methodology, as I described before, for estimate of sustainability assessment in order to make a life cycle analysis for this material. So here we have the result from PBS production by using the life cycle result from PBS production using renewable resources as raw materials. And we can see here, it depends of the indicator, we have a different results. In the case of pure glucose, because we have also the negative CO2 absorption from cultivation of sugar beet, we have a negative CO2 emissions. From corn stover, the result is 0.25 kilos of CO2 equivalents per kilo of PBS. In the case of organic fraction of municipal solid waste, this is estimated into 2.35 kilos of from kilo of BBS. So in the case of abiotic depletion, we have a better result in the case of organic fraction of municipal solid waste, which is it is 24.8 megajoules per kilo of BBS, which is lower than the other renewable resources. In the case of eutrophication, also we have better results. In acidification potential and human toxicity, the results of the environmental results from organic fraction of municipal solid waste indicates lower environmental impact. Now to continue in the sustainability assessment for utilization of organic fraction of municipal solid waste for the other marketable products, which is biosurfactant and polyurethanes. So in this case, we estimate the sustainability for the production, for the utilization of organic fraction of municipal solid waste for succinic acid, which is one of the raw materials that be used for the polyurethane production, and also the protein that can be extracted from organic fraction of municipal solid waste can be utilized for the production of biosurfactants. So we have the result as here is the whole of concept is the concept that we implement by refinery, because we can extract different products from organic fraction of municipal solid waste. So the succinic acid that produced with this way, if we take it into consideration also the biosurfactant, when we selling the biosurfactant, the minimum selling price of succinic acid can be reduced into $2.39 per kilo, without taking into consideration the biorefinery approach, and 2.14 kilo when we consider biosurfactant market price of $4.1 per kilo. And also for the polyurethanes, the minimum selling price was estimated at $1.95 per kilo. In the case of life cycle analysis for the production of polyurethanes, and by implement this biorefinery concept, so here I present a total a comparison of the total CO2 emissions that can be produced with a current scenario, which is a scenario that municipal solid waste goes for the landfilling. So we have as a fractional unit 1,000 kilos of dry organic fraction of municipal solid waste. So for the landfill, emitted into 4.2 tons of CO2 equivalents. The production of polyurethane, it is estimated with 397 kilos of polyurethane emit 1.3 tons of CO2 equivalents, and the production of 80 kilos of surfactants produce or emit approximately 170 kilos of CO2 equivalents. So in the case of biorefinery concept, we take into consideration that we have, after the hydrolysis, the remaining solid of 550 kilos of materials that can be goes also for landfilling, that emits 2.3 tons of CO2 equivalents. We have the production of 397 kilos of polyurethane that emits approximately 1.3 tons of CO2 equivalents, and also the production of 8 kilos of biosurfactant that emits 324 kilos of CO2 equivalents. The total score of biorefinery concept estimated to 3.9 tons of CO2 equivalents. That means we have a savings of 1.8 tons of CO2 equivalents in comparison with a conventional way. Thank you very much for your attention.
Thanks, Dimitris. Are there any questions? Korneel?
What does this minimum feedstock requirement mean? Is that like a minimum amount of biomass you need to make it economic?
Yes, it is related with optimum plant capacity, which is the indicator that I show you. We estimate the cost by taking into consideration different capacities. Okay. The optimum capacity, it is the capacity that the cost of manufacturing after that capacity be stable. So in this capacity, we estimate the minimum fixed requirement in order to achieve this price, this lower price.
Okay.
And this capacity.
And does that mean, according to your numbers, that like for the municipal solid waste, the minimum plant size is something like more than 1 million ton per year?
For organic fraction?
I don't know if you can quickly go back up.
1,000 is 1,140 kilotons. 1 million tons, I mean.
1 million tons.
1 million, but it is wet base. So with the 70% of this, it is...
So 300,000 ton dry matter is the minimum like plant size. Is that a realistic plant size for municipal solid waste? I wonder. Maybe FCC knows how much it is.
Per year. This is per year. This,
yeah. It sounds like a lot to me. Huh? 1 million ton is a lot.
But it's okay. It is. It is waste. I think this amount. I think it is. It's municipal solid waste is produced in the million tons. I think you can find this amount in the big countries. So here it is it's a map which illustrates, here's a map that illustrates the carbohydrate content in the different countries. So we can realize is in all the countries we have more than 100,000 kilotons. So more than 100 million tons of, it is in the most of the countries. Can be found.
These are sugars, not
yes, it is
the municipal. The organic fraction is the fraction that converts into succinic acid.
Yes, so the organic fraction will be more because this is the carbohydrate content. So that means it is quite more the organic fraction.
Is there any other question? All right, thank you, Dimitris. So I would like to welcome Narinder for presenting business models for the production of bio-based products.
Okay, hello, good afternoon, everyone. I think I'm the final presenter before lunch, so I hope your appetite for one more presentation doesn't compete with your appetite for sustaining yourself with food shortly. So I'll try and keep it as short and sweet as possible. But I'm going to talk about circular and sustainable business models, but more particularly in relevance to the LUCRA project. So at a glance, I know my colleagues have already talked about the LUCRA project in terms of what its aims are, but I'll maybe just briefly sort of glance over it again, that it's funded by the CBE program. It's running from 2023 to 2027. There's 10 partners across 7 EU countries, and the goal is to demonstrate succinic acid or bio-succinic acid production and downstream polymers production at TRL level 7, which is large pilot scale. The feedstocks we're using are the organic fraction of municipal waste and sawdust side streams. And in terms of circular business models and sustainable business models, the work packages that are relevant to that focus on that area are work package 6, which is the value chain and sustainability assessment, and then we have work package 7, which is exploitation and business models. So what we're assessing is the integrated biomass or waste or biomass to chemicals value chain. And that incorporates everything from the feedstock level, feedstocks that are provided by our partners who presented earlier, FCC, on the organic fraction of municipal waste based in Madrid, and then Montenutra or Boreal, as they're otherwise known, who provide sawdust, and they're based in Finland. They're also here today. And these we deem to be secure feedstocks and sustainable and renewable feedstocks that we're using to produce the bio-succinic acid. We have, across the value chain, a number of technologies that we're developing and scaling up. So we're looking at pre-treatments for the feedstocks, the hydrolysis of those to produce and maximize the free sugar availability, so those can then be converted to bio-succinic acid. And then we have techniques that we have a novel electrochemical membrane bioreactor technology that will produce in situ the succinic acid and also extract it to high concentrations and high purity. And then we have the downstream formulation, as Rubin mentioned earlier, for the applications in bio-based plastics and biopolymers, for polyurethane dispersions, polyesters, and potentially powder coating resins as well, and those end user applications that he mentioned as drop-in or replacement non-fossil based ingredients that can go into those products manufacture. So in terms of what we need to consider in terms of exploitable results from the project that we need to consider for the business models. So we have the feedstocks and their potential to be converted into hydrolysate and then fermented into bio-succinic acid using these novel techniques, and then across that value chain through to the end products. But then also we have to consider how those are going to be commercialized. So, whether that's something that could be licensable, and then what information is going to support that route to commercialization, so that we have the data aspects that were also presented, such as the techno-economic analysis and life cycle data that is very useful for the business models and the technology transfer packages that are essential for the next stage of commercialization. Just a bit of context, I think I mentioned earlier anyway, the work packages that were relevant to the sustainability and circularity assessment. So work package 6 focuses on that in terms of safety, sustainability and the economic assessment. And we have 2 tasks with subtasks that were involved in assessing the value chain, the feedstocks, conversion, the formulations, end of life and circularity, and then the assessment of the sustainability impact and circularity, and then also how to disseminate and communicate that. So work package 8 looks at how this important information on sustainability is then communicated to wider groups of stakeholders. So in terms of sustainable and circular, there might be a little bit of confusion as to what's the difference between one or the other. Is one more important than the other? I think they're clearly compatible in terms of the business models, but it's normally considered that sustainable business models are the overarching concept, and other models such as circular, they fit within the overarching sustainability model. And that's something that can cascade within the overarching sustainability models that are generated. But what we essentially want to achieve from creating business models is bottom line benefits, but that should be balanced with the economic, the social, and the environmental benefits and impact. But also importantly, in a sustainable business model is to have stakeholder engagement. So that also includes people that are working within that environment, so employees, the customers, and the wider community. So citizens should also be involved in that process of creating sustainable business models. And there should be long-term value creation that ensure that these business practices contribute to the long-term sustainability of that market opportunity. Other considerations around the circular business models are being resource efficient, so maximising the use of resources by keeping them in use for as long as possible, extending product life where possible, so designing products for durability, and then closing the loop in terms of having systems that can recycle back the same or alternative products, manufacturing loops. So what are the methods for implementing sustainable or circular business models? Well, I think we have to start off with defining the vision to establishing a clear and unambiguous objective in terms of your models, engage stakeholders at a very early stage, receive inputs from all, and provide feedback. Then we need a measurement of those, so measure the impact and develop the metrics that are suitable for your organisation and the products that you're doing, and then have a continuous improvement process to review and update as required. And as Rubin mentioned, they're quite on that in terms of their own internal sustainability practices, and they seem to be at the forefront of that in this industry. In terms of the circular business model, so we need to identify opportunities to look for these in production and the use of these products and services. As I mentioned earlier, design for durability. Include this in any design brief, so start early when you're designing your business models, your product portfolios, and it shouldn't be done post-design or post-product rollout, so it should be done at a very early stage. And try and implement the closed-loop system where possible, looking for opportunities to be consistent within the waste hierarchy as well. And as I mentioned earlier and re-emphasise, engagement of the right stakeholders to collaborate, co-create and maximise those opportunities. So within the context of LUCRA, if I start with the information on the right-hand side, the core technology highlights in terms of what we try to achieve in terms of improving the operational performance. So we try to achieve thermal and enzymatic hydrolysis processes to produce high purity sugar streams, free sugars that can be used to produce the succinic acid efficiently. And then we've got the novel techniques that not only are efficient in producing biosuccinic acid, but also reducing fossil-based chemical consumables usage, such as sodium hydroxide. So we had some targets that were set out at the beginning of the project to achieve, greater than 50% reduction in caustic usage, and also other targets around reducing the amount of greenhouse gases that are producing. So having integrated demonstrator lines that would reduce greenhouse gases. We're also obviously measuring that in the project. So the work that Dimitrios is doing on the LCA and TEA analysis is assessing that at the moment. And then the scalability. So we're producing at cubic meter scale the hydrolyzers and fermenters for the production of succinic acid, and Biobased Europe pilot plant are doing that within the project, and we're almost at that stage where we're starting that scale up now within the project. In terms of some of the product and service portfolio targets, so at the beginning of the project, we were targeting the minimum selling price of €2.5 per kilogram, so that's pretty close to what Dimitrios has just talked about in terms of the minimum selling price that he's been measuring in his assessments. At the start of the project, we were talking about 40,000 tonnes of material capacity. So obviously that's with organic fraction, but we're also talking about sawdust as well. So we have some flexibility there in terms of capacity when we're looking at different feedstocks. 60% renewable carbon content in the end products. Technology licensing and the engineering services that are required for the biorefinery. So those are key considerations in our business models. And then having a co-development program with the brand owners for sort of green coatings and plastics. And all of that supported again by essential data such as the life cycle, the carbon analysis and the TEAs. There are a number of templates that can be used that are freely available. This one is from KISS, which is Keep It Short and Simple. And this is a circular business model canvas that can be used to capture key information around those circular business models. A lot of the information is fairly standard from the business model canvas that's readily available, but these are sort of free to use. And you can download these from these websites. Another one, this one is a sustainable business canvas. So this is around the sustainable development goals. Very familiar format in terms of the key information that needs to be collected around the key partners that are involved, the activities, the unique value proposition, customer relationships, resources, etc., cost structures. So you'd find in a standard business canvas. This is something that we are developing in the LUCRA project. So just some information there that's relevant to the bio-succinic acid production business model canvas. We have key partners from the feedstock chain and sort of chemical off-takers. And then we have key activities around the development of processes around valorizing and producing the bio-succinic acid formulations. And then we have customer segments that are in place as well. So we've looked at the entire value chain, and I think we've covered it quite well in the LUCRA project with targets that are competitive on a commercial basis, and whilst trying to achieve realistic targets for scale-up as well. And there are a number of business model typologies that we're investigating in Work Package 7 for the exploitation plans. They include in-house upgrades of processes, standalone biorefineries, cooperative ownership and license plant, and regional industry clusters. So we're looking at all of these as potential business models for the production and under a biorefinery concept. In terms of, if you want to understand a little bit more about the circular economy categorization, there's 14 categories grouped into 4 high-level systems. So starting with design and production, so circular design models, design the products and materials with the aim of long-term value retention. The optimal use model, support better usage and supporting services. Value recovery, so capture value after the user's life. And then the support structures as well. So there you have the traditional hierarchy of retail, assembly, manufacturing and extraction, or repair, reuse, refurbish, remanufacture, recycle, and hopefully not, but yeah, landfill as a sort of last resort. Within the LUCRA project, we have defined value propositions that we're either trying to meet or beat in our route to commercialization. and our roadmap to commercial success. And we want to be competitive on price parity with fossil succinic acid production post-project. We want to have a good payback period of around sort of 6 years. We want to achieve 50% greenhouse gas reduction, VOC-free formulations to meet the EU Green Deal targets, early stage MOUs with coatings and polymer converters when we're at that stage that we believe we can meet the specifications that are required. And then in the future, we'll look at ongoing opportunities for further funding, whether that's through a flagship type project or private investment to scale up to commercialization. Another important aspect is the EU taxonomy for sustainable and circular activities. So we need to ensure that we meet the requirements for that. There are tools that will help and support that. So there's a website here that I've put up that provides information on the tools and standards around the EU taxonomy. But the principles are that we need to achieve environmental sustainability, economic growth, and social benefits as well. So we will measure that and ensure that we achieve those goals within the project too. Where we are aligned with the EU taxonomy and sustainable development goals, so we believe we have an opportunity to have a substantial contribution to climate change mitigation, do no significant harm by valorizing waste and reducing fossil-based chemical usage, being responsible in terms of consumption and production, and then also being innovative in the way that we are producing our products and creating infrastructure, and also meeting our climate action targets. I think that's the end of my presentation. Thank you.
Thank you, Narinder, for the guidance on the requirements for business model development. Are there any questions from the audience? So if there are no questions, I think we can thank first Narinder for the presentation once more. And we can have a short coffee break at this until we set the stage for the round table. Okay, so 10 minutes of coffee break. So I think that was a very interesting event presenting opportunities to develop bio-based products and also utilizing bio-based feedstocks for the production for the bioeconomy era. Now, I would like to welcome our speakers in the panel, which I would like to ask some questions related to the potential to develop bioeconomy products from biological resources. Starting actually from Marina, I would like to ask you, which are the major current limitations for industrial implementation of bioeconomy products? Ah, yes.
Okay, thank you.
Thank you.
I chose this question because I think I have talked about this a little bit before during my presentation, but maybe at this time I could explain it a little bit more. In our case, the main challenge, as I said before, is to face the actual currently regulations. We have no clear regulations about bioeconomy in Spain and especially in Madrid. So I think we need to improve the regulations in order to have a model that allows us to have a real circular economy. Because as we were talking before, we depend a lot of landfills because of people, because they want solutions, but they don't want biogas, they don't want incineration, they don't want anything. They want circular economy. So maybe if the laws allows us and permits us to do these needs more clear and they help us with a clear law, maybe we can face this challenge. We could face this challenge better.
Okay, thank you very much. I would actually like to ask the same question to Tanja, who is representative for research and development entity, regarding also how research institution industrial partners could collaborate in the development of bringing pilot projects into commercialization.
Yeah. So Apostolis, I think there are like different aspects to consider. Like, for example, one is the organizational setup, like the different nature of like a research institute or industrial partner. So basically, for technology transfer, it could be an option to have like LUCRA, a joint collaboration project based on public funding. So the research organization or from, let's say, academic partner side, administrative hurdles can be addressed, whereas like from startups or SMEs, so the industrial side, they can support with the technology development. So there are like really different mindsets that basically come together, and it has to set up some trust, some long-term collaboration. Maybe the industry can give some guidance on where the research should go. Research staff or personnel should need to understand what are the market requirements, what are the industry needs requirements. The timeline of such a collaboration or project should be considered in terms of, yeah, it needs to be implemented quickly because every second is money for an industry partner. So these different mindsets, building up a business mindset for economics and for scale-up are some consideration points. And what I think is also very helpful is to use intermediaries, like a cluster or networks or association that have the very specific expertise how to bring academic or research institutions together with industrial partners and to help in terms of technology transfer, and then also to help, yeah, what we call the crossing the valley of the death, from where the CAPEX and OPEX requirements are going up when you go from academia to more commercializing innovation, and the risk of the technology itself that come from the research base is still very high as well. So, yeah, finding this bridge from academia, research level to industry through collaboration, through co-creation, through trust building, I think is a very important factor.
Regulation legislation?
Sorry?
Regulation legislation is also a requirement for further improvements and amendments.
Yeah, because indeed, at lab scale, let's say, when we still talk at academia or research level lab scale, there are different regulations if you go into production, manufacturing, commercialization lines. So if the market entry step with the second valley of death, for example, that are completely different. So indeed, that's another point where two different worlds need to come together and find a common strategy and vision. No?
Thank you very much, Tanja. I would like now to move to Korneel. I think you are an example of an academic that turned entrepreneur So you have a very good feeling about what is needed in order to convert a research technology into practice. So I would like to ask you, what is needed in order to scale up technologies based also on your research and your recent company experience, in order to make this sustainable and feasible in terms of efficiency and cost?
Okay, it's a pretty broad question, but thinking about it, what you're trying to do here is to use undervalued side streams to make a product that hopefully has a high value. But to have that high value, there's always the two requirements, right? The product needs to be of a sufficient quality and a consistent quality through the year. You cannot allow for variations. And the second thing is you need to have sufficient scale to make the product. So you really need to scale up. The thing is that these two parameters are not very compatible with biomass streams that are typically distributed, and transport is very prohibitive. So in order to scale up, you're going to need, to my opinion, a hybrid model where you have a more centralized production facility where your last steps of production are happening and the expensive steps of purification and certification. Everything you can do before that, you better do locally, like local processing of the biomass into a stream that is transportable and economic to transport. The advantage of such a hub and spoke model is that you can locally build smaller and faster, build these installations, and also fine-tune locally the treatment that is needed to deal with the fact that in different locations the feedstock is different. It's an illusion to try always everything in one place. They've seen that like in Denmark, where they wanted to make a huge ethanol plant from wheat straw, and then over the year the wheat straw was changing composition, and at that scale changing your front end is just not economic. So if you have distributed processing, you don't need to scale up very much. You generate a concentrated intermediate product, and then centrally you scale up, but then you go into a scale up that is more with conventional technologies for a good part. And so to me that's a key, is to start with modular systems around. It will move faster, and 10 small systems are also a large system, and that also makes economic sense to me. So the example here, like the municipal solid waste, you rarely have 1 million tons of that material somewhere. It's more distributed, a few thousand tons here and there. So make something concentrated from that, like a sugar solution, whatever, concentrated sugar solution that you can transport, and then centrally you can have the quality and the consistency of the product. Yeah.
Actually, I think this makes sense, that because nowadays what is used is glucose syrup produced mainly by companies like Cargill, utilizing corn in order to produce the glucose syrup, which is transported to biotechnology companies to produce fermentation products. So this is a similar concept, producing the sugars at different locations and transporting to the fermentation sites.
Yeah, it also avoids a lot of implementation issues. Getting permits for large installations is very hard. Getting a smaller plant locally up is much less sensitive in terms of getting permits, if getting also the general public on board, that there's only small plants. And then centrally, really in industrial areas, that's where you do your larger scale production. And indeed, the more you can get sugar solutions that look like what industry is using today, yeah, the better, of course. We should minimize the diverting away from what is currently being used in industry.
I think this is also important for creating industrial synergies and distributing the market from feedstock production to intermediate production and final product production. Yeah. It's similar to what is happening today, actually, with petroleum refining.
Yeah, yeah. A last item that's also important, and this is maybe more my pet peeve, but what is forgotten massively in industrial biotechnology and production is the water. the use of acid base, the salt ending up in the water, creation of brines and wastewaters is generally like left a little bit like, oh, we'll deal with that later. You don't deal with that later. There's new EU regulation going to come on brines. And you know that if there's more than 0.5 gram per liter of salt in water, it's technically no more fresh water, which means if you have an inland plant and you use acid and base, you are no longer discharging fresh water in a freshwater environment. And this is going to bite very badly. So how to deal with the water is something to look into with a lot of urgency, because it's going to be a showstopper. There is going to be legislation of a model that says that, well, you know, if you have an industrial processing, then you cannot put more salt into the environment than you pulled out with the water that you took in. And that's really, if you look at many industrial production processes, going to be a showstopper that's going to hit us. Yeah.
Thank you, Korneel. Now I would like to move to the two industry representatives, starting from Dimitris from HIMAR. And I would like to ask you about the major technical and economic challenges associated with the establishment of bio-based adhesives in the market that HIMAR represents.
Okay, so now we're in a phase in the sector that more bio-based solutions are commercially available, and many producers have products with bio-based solutions. But the major challenge with bio-based adhesives is, of course, the cost, but it is directly connected to the performance. Because if I use 10% of urea formaldehyde resin and I use 5% of bio-based adhesive, but it has the twice the price, then it is the same for me. But if I use the same quantity in order to achieve the same performance, but I have a double price, then it's very difficult for the industry to implement these solutions. Also, now a big challenge for the sector is the recycling of these panels after their end of life. So now a lot of board producers, instead of buying fresh wood, they buy or they have recycled panels from furniture and other desks and whatever. But in order to use this material, maybe they have to increase the resin they apply, or maybe they have problems with the formaldehyde emissions, which are very strictly regulated in the European Union. But these producers, they don't have any incentives from the regulations to use this material. So instead of buying fresh wood, they buy these boards, but they need to spend more money in order to have a good product. So I think also we need to have some legislation and regulation to promote the use of these materials in the industry.
However, if you increase the bio-based content, you reduce the CO2 emissions. How does this affect the CO2 charges based on the current legislation? Does it reduce the overall cost if you include also the CO2 emissions, or it does not affect it in bio-based adhesives?
I don't think it's you can sell the board on a better price. I think now it's more each company wants to go greener, so they promote that they have a board that it's more green, so less carbon footprint. But I don't think that now they have any price difference in the market.
Thank you very much, Dimitris. I would like to ask actually the same question to Robin, as a representative from Convestro, a multinational on polyurethane production. So I would like to ask the same question about bio-based polyurethanes. What do you think about the barriers, economic or legislative or environmental, for growing the market of bio-based polyurethanes?
Yes, in principle, it doesn't matter from which source, and we have to face the brutal truth. One is the skill, and how much skill we are talking about. The skill of economy we are talking about small scale is always less competitive than large scale. Another is the price. So price is very important, not only for Covestro and also for end user, for consumers like you and me. It's nice to have this bio-based or bio-based material or anything, but the customer, they have to be willing to pay more. That is a dilemma at the moment, and every company is facing pressure to develop something which is bio-based or renewable circular economy, but everything comes with a price. At the end, the price must be consumed by us, you and me as a consumer. That is a barrier and also a challenge for every company, how to promote this technology to the market.
For Covestro, how feasible is, for instance, to substitute adipic acid to succinic acid? It depends on the properties, it depends on the availability, it depends on the bio-based nature of succinic acid. So what you mentioned also applied to succinic acid, or there are also some other requirements for the adoption of succinic acid as a substitute to adipic acid?
Yeah, in principle, succinic acid is a very small part within Covestro. Adipic acid is far much bigger than succinic acid because of the properties of at the end polyurethane dispersion. Is all about your polyol, which polyol you use. And the good news for Covestro, we are the producer of isocyanate, and so we can fine-tune this the structure of this cross-linker together with the polyols, but succinic acid is still by far is not the biggest within Covestro. As I said, one is a property and another is the scale, because currently the succinic acid bio-based is not new, and in the market is already existing. Bio-succinium used to be from DSM, now it's a spin-off or it's a sold-out license. As in Belgium, they are producing, or in France, this is a bio-based succinic acid. So scale is not big, price also not really competitive with the fossil-based.
Okay, thanks. Now I would like to ask one question to Professor Briassoulis regarding the end-of-life recycling schemes. And we can focus on either food packaging or agricultural plastics. So there is a discussion relating on the by design development of plastics, depending on the final product and the requirements. What is, because you are a scientist, yet you have been involved in research projects and you have also very good knowledge about the relevant legislation. What do you think are the main barriers to adapt such solutions that will incorporate biodegradability and bio-based nature based on the current legislation? What changes, amendments are needed?
How many questions are there?
One.
About what?
About the amendments of the current legislation as related to the final requirements. Is there any specific amendment that is needed or some specific amendments that are needed to be implemented?
Sorry, I'm lost. For which application?
Let's say about plastics for agriculture.
In general, or for mulch and film?
Mulch films, let's say mulch film.
For mulch and film, there is a long history, but there was a lot of pressure the last decades because it has been proven that the use of conventional mulch and films, which helped a lot the farmers in terms of suppressing winds development, in terms of conserving water. The farmers were happy because the cost of the production, for example, horticultural production, vegetables, strawberries, so on, was very good for them. But the end of life of these films had no solution, as I mentioned before, because they cannot be recycled. They are very thin, and they are heavily polluted, and the recyclers do not accept them. Or if they are considered in terms of logistics, that in this area we collect mulch and films for recycling, what was happening several years ago, but until recently, was that recyclers had the benefit of subsidies for recycling, but they did not recycle finally these materials, but they were selling them to China, or they were cheating the system, to say it simply. So the development of biodegradable mulch and film, biodegradable soil, was the only solution practically. This is why it has been developed by in few compositions in terms of polymers and additives, but at least 2 or 3 commercial products are now used extensively, despite the fact that their price is, let's say, 2 to 3 times higher than that of the conventional films. But on the other hand, they are of lower weight because of thinner films, and they have no cost for the management. Until the legislation for the waste management of the conventional film is imposed, which means the polluter pays, the farmers will continue to use the conventional mulch films, thinking that this is the cheapest way, and they do not care even if they rototill this degraded by sun UV radiation films into their soil, their property, polluting their soil as a production means, because incorporating polyethylene microfragments in the soil changes very important characteristics of the soil. For example, drainage capacity and so on. So there are still problems in the wider implementation of biodegradable mulch and film. This is one of them. Another one from a recent project we have identified is that if you use the biodegradable mulch and film that I showed you, it disintegrates fully in 5 to 7 months. In Finland, in a similar experiment in Finland with the same mulch and film, in Finland you have 5 months with sub-zero temperatures in the soil during the winter. In addition, the soil characteristics in this region, and in general in this northern part of Europe, Scandinavia, the soil pH is acidic, make the soil acidic. The acidic soil has been shown to have inhibition behavior against microbial activities, including disintegration, biodegradation of organic matter, and also of mulch and film. And this problem cannot be solved by using mulch and films, biodegradable soil according to standard specifications, but the solution needs the development of innovative new materials, biodegradable in acidic soil, at more easily biodegradable at lower temperatures, so that there is a need for new products in the market designed specifically for different applications.
So the complexity is very high and should be implemented per case. case-specific. So we need to develop case-specific applications. So this is not a solution that can be given in a generic manner. It has to be guided by the product and the conditions of each case that the solution should be applied. So I would like to thank you all for participating in the panel. I would like to thank you everyone for the participation in the workshop. I think we have concluded the workshop. I'm very happy, and I would like to thank also the municipality of Chania, the DEDISA, for making this possible. And I hope that we can have a long-lasting collaboration with the DEDISA and all the partners in the landfill, CIRC landfill project and also the LUCRA project. Thank you very much.